information were transferred to.
Yeah, actually, we found it's very on semantics. Okay, when it also has taken
Or at least the step.
yeah, at least we found that in the next, right, that we're saying. And we also look at the morphology. We say we look at single point because otherwise we couldn't read. They kind of like there's steps in that given layer.
Okay.
So basically, you can think of like given layers kind of like they or what you kind of unit is like we can kind of like one thing you move projectly on some those and then you have the hardware different space. See, another thing you want because otherwise you will look like different. Yeah. When it's sort of the selection of the
Okay, then for a more for the language case,
Yeah.
so like, for example, as a like a single LLM,
yeah.
then each of the generation step, all we have observed is now the like open models, they start to have more and more like higher dimension like
Right.
tokenized like more tokens.
Yes.
And then this into like Gemini and then Llama 3 and all stem from there's like 30K to like 200K. So they expand that. So that correspond or related to is kind of
So
you don't want it to be less or
this is actually very interesting point. Actually, maybe I want to ask you that we are also trying to look into more expansion. What is the question from? I mean, what is the better software? So typically when we like we only reach the minimum layer, we also make this like a wider what people got.
Yeah. So those like usually the gaps and the rest like they go there, but I'm more interested in when I face the
See if we can get started. Okay, let's resume. So my name is Qing. I'm from University of Michigan. So this is last lecture of this morning session. So in the last tutorial, I want to talk about something about this invariant low-dimensional subspace structures when learning deep neural networks. So and for the afternoon session, it will resume at 1:30. So in this session, I will continue what Zhihui has talked about, where Zhihui is majorly focusing on the last layer representation of a neural network, right? So in this talk, I will first to shed some light about the structures of this kind of intermediate layers, how this neural collapse happens from shallow to deep layers, and what kind of geometric structures in the representations in the intermediate layers. And secondly, this kind of structure actually strongly correlates with the structures, learning dynamics in the weights. Actually, the weights and the representations, they are dual to each other. So if the representations have this kind of neural cloud structures, then this suggests that the weights of the neural network we learned also have is structured. And I'll try to shed some light on the structures in the weights we are learning this kind of a neural network. And once we do this, so in the third part, I will talk about how can we leverage the structures in the weights to do network compression and how to do fine-tuning, efficient fine-tuning of neural network, right? This kind of low-rank adaptation approach. So that's the structure. So let's first continue what we talked about this neural collapse, right? So we know that from last lecture, right? The neural collapse is a phenomenon happening in multi-class classification problem, right? So we looked into the representations of the neural network in the last layer before the linear classifier, and we know that the neural collapse is basically kind of a memorization or overfitting phenomenon that the last layer representation actually are collapsing. They are collapsing when the training converges, right? The last layer representation, they will collapse to a one-dimensional representation for each class. And this happens prevalently across all kinds of network architectures like ResNet, MLP, VGG, and even on transformers. And how can we quantify neural collapse? Zhihui have talked about the experiments, but he here, let me rigorously define how can we capture this kind of collapsing phenomenon by this NC1 metric. So through this animation, we know that the last layer representation, right? When the training converges, right, for each class, the feature will be a one-dimensional. Basically, all the representation in that class will be concentrating to their class means, right? And to quantify this, we can define a NC1 metric. This NC1 metric is basically trying to measure the compression of the feature, how concentrate your feature for all the samples, for all the training samples to the class mean. So this is quantified by two quantities. One is between class covariance matrix. The second is within class covariance matrix. So the important part is this within class covariance matrix. It measures how the feature Z are concentrating to the mean. So here Z bar denotes the mean of that class. And this between class covariance matrix basically is acting as a normalization factor. And you take a trace of this, right? It's basically measuring how the representation is concentrating to Z bar, the feature mean, right? If this trace is smaller, it suggests that your feature are more collapsed. And we know that neural collapse means that the features, the NC1, actually collapse to almost zero. But how about the intermediate features? How about the features in the intermediate layers? And if you measure the NC1 on the intermediate layers, you can see that actually this NC1 is collapsing progressively from shallow to deep layers, right? So this x-axis is the number of layers, and the y-axis here is taking a log of NC1, right? And you can see that actually there's almost a linear trend from the shallow to the first layer to the last layer, right? And indeed we test this on both like linear network where we get rid of all the nonlinearities, and we test this on nonlinear network, and we try to measure this feature separation and concentration of this NC1, and to see the trend, how this is happening from shallow to deep layers. And you can see that the right plot is when we measure this on MLP with RaLu activations, and you can see that actually this NC1 has this kind of geometric decay from shallow to deep layers, right? It's approximately geometric decay from shallow to deep layers. And if you measure this on linear network, right? Here, what I mean linear network is basically you're removing all the, you're just replacing the RaLu with a linear activation. And you can see that actually this is exactly, there's a geometric decay of this NC1 from the first layer until the last layer. And that's why this kind of neural collapse happens upon the last layer, right? So there's a progressive neural collapse happening from shallow to deep layers. And actually there's a rate of convergence of this kind of decay, right? With a linear rate of convergence. So this inspires us, right? So if we want to understand why this kind of neural collapse or progressive neural collapse happens, this similarity between linear networks and nonlinear networks inspire us to first look into what happens in linear networks, right? And so here, what I mean linear network is basically we get rid of all the nonlinearity, and we just consider a linear network, deep linear network like this. And then for simplicity, we just consider training this using like a MSE loss. So here you may ask, right? So why do we care about like linear models, right? So here I think the power of a nonlinear network is that because of nonlinearity, right? You're using a lot of nonlinear activations that to transform nonlinear data to be linearly separable. But here, why do you just consider the simple linear network? Because eventually this linear network is just a linear transformation, right? It cannot separate nonlinear data. But it turns out that actually the first several layers of nonlinear network is kind of doing increasing your linear separability. And actually the deeper layers, they are acting a lot like linear networks. They're basically doing linear feature compression. So here, to illustrate this point, we did some like comparable experiment. So what this experiment did is that for this figure, what we did is that we did an experiment on nonlinear MLP network with a RaLu activation. And we measure the linear separability about each layer. So basically what we do is that we train a nonlinear network, and then upon each layer, we do linear probing. We use a linear classifier to test on the training data set what's the linear classification accuracy upon each layer. And for this nonlinear network, what you can see is that initially, right, so the linear separability of your features is increasing dramatically at the initial sublayers. And then it saturates from the third layer to the last layer. So the linear separability actually doesn't increase much. And so the red and green curve is measuring the feature compression. So basically we measure the feature compression by measuring the numerical rank of your features. And you can see that for the initial sublayers, right, the numerical rank increase a little bit, but it doesn't change much when when the linear separability is increasing, right? And then it switches the goal, right? So from the third layer, where we centralize the linear separability, the feature compression takes over. And you can see that actually the feature are actually compressing because the numerical rank is dropping, right? And you can see that actually the feature rank, I mean, we are compressing the features onto the last layer, and that's why the eventually neural collapse happens. And for comparison experiment, we did a hybrid network. And the reason we want to do a hybrid network is because if you look at the linear separability, right? So the initial third layer, the initial several layers, actually dramatically increases the linear separability. So what if we use the initial two layer or third layer as a nonlinear network, and we use the last few layers completely replace it by a linear network? What will happen? And actually, the trend is very similar, right? So the first several layers, we use like a nonlinear activation, but the last several layers, right, we're just using linear network. And this is a comparable experiment versus a purely nonlinear network. And you can see that the first layer, several layers, is indeed increasing linear separability. And then the linear network can also mimic the role of a nonlinear network in terms of feature compression, right? It's progressively compressing your features until the end, and also the neural collapse happens at the end. So this suggests that if you study like linear network, right, it cannot fully explain what happens in nonlinear network, but it can provide some insights what is happening in the last several layers of a neural network, right? Actually, the last several layers of neural network, there's a lot of linearity behaviors in that. And this is a visualization of the UMAP visualization of the features on CIFAR dataset. And here, this is showing the first row is showing the nonlinear network, right? And the second row is showing you a hybrid network of first several layers is MLP with RaLu, and the last few layers is linear network. And you can see that actually the feature map it looks kind of very similar. So a final question is that you might ask is that, so the linear network, you look at is it just a linear transformation, right? Why not you just using one layer? And how does this depth in linear network helps? Eventually, it's just a one-to-one like a transformation, right? Why you want to so many layers of this kind of a linear network? And it turns out, right, the depth actually helps you with the feature compression, right? If you don't have depth, you don't have enough feature compression. And if you have the depth, even in linear network, it helps you to compress your features per layer. And this helps with generalization, right? So here, this is a plot that we're showing the test accuracy when we're using a hybrid network. And when you're increasing the layers of this kind of the linear component, right? You can see that actually this test accuracy increases a bit. And actually, this is because you are compressing your feature more using the number of layers, right? And so this gives you a motivation that why we started this kind of a deep linear network. So next, I want to introduce some theoretical results. And actually, we can, based on linear network, we can capture, rigorously analyze, so what's the compression ratio from the first layer to the last layer. Remember that even on linear networks, right, the features actually, there's a geometric decay of the features from the first to last layer. Right, we study a simple classification problem, right? And we also using this a variant of NC1 metric to measure the feature compression for each layer, right? This is a definition of a feature compression of each layer. So basically, we take the trace of this covariance matrix of within class means, right? Divided by the trace between or the between class covariance means as a normalization factor. And we also measure the feature discrimination. Basically, we just measure how separated the feature means to each other. And based on this, right, and then you can visualize this kind of a feature compression, right? You can see that for the first row is showing you on this linear network, and the second row is showing you this feature compression on nonlinear network. And you can see that actually there's indeed a geometric decay of this NC1 or this variant of NC1, this CL, this feature compression metric, right? There's a geometric decay from the first to last layer. And this is the trend is very similar on both this linear network and this nonlinear network. And for feature discrimination, right, we can show that actually the feature discrimination for the across the layers, right, the feature is becoming more and more discriminative from the shallow to deeper layers, right? And actually, if we make certain assumptions on the data and the trend weights, we can rigorously characterize the convergence rate of the feature. So I will talk about, let's see if there's some issue on this. Doesn't work. Stop working. Yes, okay. So I will talk about this assumptions on the weights later on. So actually there's a kind of low rank structures in the weights actually leads to the results in such a theorem. What we showed is that actually we can rigorously capture the feature compression, right? We can show that the features are indeed compressing with a geometric decay rate, where the decay rate actually depends on the initialization of your weights. Here, this epsilon is the initialization scale of your weights. And actually, the decay actually is a geometric, right? The geometric decay. And this is a upper and lower bound of this decay ratio. And we can verify our theorem through experiments, right? This is a upper bound and a lower bound, right? It captures this kind of a linear decay rate of this kind of feature compression. And So, and we can show that actually this phenomenon doesn't only pertain to the assumptions we made in our theorem. So we considered different initialization types. We consider different initialization scales, right? You can see that actually there's the exact like linear decay rate, right, captured by our theorem. And so we also demonstrate on the real data sets, right, by training this linear network on fashion MNIST and CIFAR, right? You can see that exactly there's a linear decay rate where if you have more layers, right, you have more collapse and decay until the last layer. So this can have some implications when you're doing transfer learning, right? So we know that if the features have this kind of a progressive decay, then why maybe a good and we know that when you use the feature upon the last layer, right, you lose all the information of your input data, right? And that's kind of memorization phenomenon. So instead, why not, if you want to use some features that keeps the information of your input data, why not you use intermediate layers? Because when you do transfer learning, right, you don't want to lose all the information of your input data. You want to preserve some information. So that's how that people typically, there's a strategy when doing transfer learning is that the adding a projection head when you pre-train the model, right? You add some dense layers before the linear classifier. And so this is a called projection head. Those dense layers are called projection head. And you can expect at the end of this dense layers, right, neural collapse happens. But in the intermediate layer, right, the feature will be not collapsing, and actually they will have better transferability. And we demonstrate this, right? This is a number. So this plot is showing the number of projection head you are using, and the y-axis is showing you the transfer accuracy. And you can see that if you're using more projection head, right, you have less collapse, and you have a better transfer accuracy, right? And this gives you a validation why we are using this projection head when do transfer learning or unsupervised, self-supervised learning. So next, so this is all about the representations, right? And here in this part, we give some insights of why progressive, like we characterize this kind of progressive neural collapse. But why this kind of progressive neural collapse happens? So our intuition is that the representation and the weights, actually they are dual to each other, right? So if the representation have structures, they mean that the weights are also structured. And actually we can show that the weights have this kind of low rank structures. And actually we show that this kind of low rank structures, actually there's an invariant subset structures in the weights when you're training them. So this is a phenomenon I want to show you. So here, what we did in this experiment is that we tried all different kind of models, like MLP, VGG, and vision transformers. Here, what we did is that we plot the singular value decomposition of the weights about the last layer, and so for the weights in terms of the last layer, so here we sort the singular values from the largest to the smallest. And so the x-axis is a singular value index, and the y index is a number of iterations, right? So what you can observe from this figure is that so first of all, this updates, this gradient updates delta W is very low rank, right? If you look at one iteration, the singular values are concentrated on few indexes. And second, we can observe is that actually there's an invariant subspace structures. So which means that actually this gradient descent only updates a small subspace within the weight matrices, right? And the subspace is invariant across the index, right? And this is also true, and not only true in training your models, but actually this is also true when fine-tuning your models, right? So here, this is another experiment we did, is that when we fine-tuning the BERT, this kind of models on this glue data set. And so this is the fine-tuned weights. And we're also trying to visualize the singular value index. So here, the x-axis is a singular value index. And the y-axis here instead is adapted layers, right? And you can see that actually for all the adapted layers, actually the delta W, where you fine-tune, actually is very low rank, right? And if you, on the other hand, so this fine-tuning also happens in invariant subspace. So here we are, this middle plot is showing you the angle between the initial weights or the weights at the case iteration versus the converged weights, right? So here the cosine angle is measuring the converged weights between versus the teeth iteration weights, right? And you can see that actually in the initial sublayers, right? Actually there's a dramatic change of the subspace. But when the training stabilize, so actually the updates is doesn't is happening within the same subspace, right? Because the cosine angle is always one, right? It doesn't go out of the small subspace. In the meanwhile, even the subspace doesn't change. If you look at the training loss, right? The training loss in this stage is still decreasing, right? So this suggests that when you're training those neural networks or fine-tuning the networks, actually the weights is pretty low rank. And also, this training dynamics could happen, especially in the deeper layers. It's happening within a small invariant subspaces of the weights. So in the second part, I want to build a theorem to capture this result on a simple neural network, which is again this deep linear network. And we'll show that actually when you're training the deep linear network, actually we can exactly show a theorem that the training only happens within a small invariant subspace of the weights. So the setup is similar. So here we consider the X is our input data, Y is the labels, and we just consider a linear network by getting rid of all the nonlinear activation functions. And we consider a setting that just is a simple MSE loss. But in practice, we find that even you training or fine-tuning on cross-entropy type of loss, this kind of invariant subspace could still happen. And for theoretical study, here we consider orthogonal initializations, right? So we consider the initialization here orthogonal, the weights are orthogonal. And here the epsilon is our initialization scale. And so here we are using small epsilon initialization scales. So here the epsilon is small, and I will talk why later. And we consider a simple gradient descent learning dynamics. And starting from this initialization, we update the weights using gradient descent. So here, one caveat is that we also consider weight decay, right? Basically L2 regularization on the weights. Here, the lambda controls the weight decay, and alpha controls your learning step. And so the difference from all the previous works that analyze the gradient descent or this kind of learning dynamics on this kind of training neural networks is that we also consider this kind of low dimensional structures into our data, right? So here, if you consider, say, for example, classification problem, right? So your labels are one-hot labels, and in that case, the Y matrix is kind of very wide matrix, right? And it's kind of very structured. And actually, there's the number of rows is much smaller than the number of columns. And if you consider some like low rank matrix recovery problem, right? So the Y matrix actually can be very low rank. It's very structured. And if you incorporate this kind of structures into your analysis of the learning dynamics, actually you can show that if even you consider linear networks, right? The training, you can show the weights is very low rank, and there's an invariant subspace structures in the weights. So here, this is an experiment I want to illustrate my point. So here what we did is that we train a three-layer linear network. And here, this is a visualization, a singular value decomposition visualization of the first layer weights. And what I'm showing here is that if you look at the left figure is showing you the singular value index, right? So the singular values where the x-axis again is the singular values sorted from the largest to the smallest, and the y-axis is showing you the number of iterations, and the z-axis is showing you the magnitude of the singular value of the weight matrix. And what you can observe is that across a number of iterations, right, the singular values only changes for the first three and the last three, right? And here we assume the rank of y is equal to 3, right? And for the rest of the singular values, they are totally unchanged, right? They are totally unchanged. And so this is only about singular values. How about the singular vectors? Here for the singular vectors, what we are measuring is that for each singular vector, we measure the angle between the initial singular vector versus the singular vector iteration t, right? And then you can see that actually, again, the singular vectors only changes in the dominant and the smallest subspaces, right? The majority of the singular vectors actually doesn't change. And this is true for the left and the right singular vectors. And this is about the first layer. So how about other layers, right? So actually you can visualize this on every layer. And you can see that for linear networks, at least for linear networks, this invariant subspace actually happens for every layer, right? You can see that the updates only happens within these small invariant subspace structures. And actually another thing I want to mention is that, so here, the values, the unchanged values of the weights actually depends on your initialization scale. If your initialization scale is small, then this means that those unchanged singular values actually could be very small. Then this suggests that actually your weights is pretty low rank, right? When during training. And so this is a visualization to give you some intuition here, but actually you can rigorously prove this. And what you can show is that, so consider that your outlier neural network, linear network, and you assume that the data satisfies certain assumptions. And actually you can show there exists a left and right matrix like this. And for each layer of the weights, and at every iteration, you can decompose your weights in a way like this. And this is true for every layer, right? So you can see that actually, sorry. So you can see that actually you can decompose a matrix into a form like this, right? And this W tilde L, actually this is your compressed weights of size 2R by 2R, where this compressed weights is the intrinsic dimension is depending on the dimension of your input and output data. And you can furthermore decompose this WL tilde doing a singular value decomposition, and you can plug this WL tilde back to this decomposition, and you can see exactly that the plot I showed you previously is true, right? So if you plug this singular value decomposition of this compressed weights into the decomposition, and you can see that the weights, the updates of the right singular value is only happening within a small subspace. The right singular value vector is also happening within a small subspace. And the singular values only changes for this dominant 2R size. And for the rest of singular values, actually if you don't use weight decay, they are totally unchanged, right? If you use weight decay, this rho actually will be converging to 0. And this rho, if you don't use weight decay, actually will be proportional to your initialization scale. So if you use a very small initialization, so which means that the rest of singular values actually could be pretty small. Right. So the implication here is that, right, so there's a lot of redundancies in your weights, right? There's a lot of the weights are totally unchanged, right? So this is WL2 and VL2, right? They are totally unchanged during the training. So this means that maybe we can just compress your learning dynamics to do low rank training of your weights, right? Secondly, if you're using small initialization, so this suggests that actually the weights of each layer is very low rank, right? So the low rankness, so this actually suggests that there's a lot of existing work, like saying that there's an implicit low rank bias in your embedding your learned representations but actually I think we can show this low rank bias or this kind of low rank bias is explicit during your whole training dynamics, right? If you use more initialization, right, each layer of the weights actually is very low rank, right? And moreover, we can show that this kind of invariant subspace structures is true in more generic settings beyond what we proved. So here, what we proved is that our input data is near orthogonal, but if you use the data that not whitened, this is also true, right? This is the invariant subspace structures. And in practice, people also use Adam type of methods other than gradient descent, right? You add a momentum to your learning dynamics. And it turns out that even you adding a momentum, and this kind of invariant subspace structures is still holding here, right? So next, based on this theorem that we prove here, I want to show you that how can we use such a property to do low rank training, right? How can we just get rid of the redundancies to compress your learning dynamics to make your training more efficient? And this also can be applied to fine tuning, right? Low rank adaptation, this kind of LoRa type of idea. And actually, by using such idea that we showed here, we can improve LoRa, and we can propose a method called deep LoRa, and actually we can automatically select the rank to in LoRa that prevents overfitting when we fine tuning on low short or few short regimes. So I want to start with something simple to build up the intuitions. And then I will go to fine tuning, like using LoRa type of ideas, that how this kind of idea can be leads to better fine tuning strategies beyond LoRa. So the starting point is this very vanilla problem called deep matrix completion. And this is a problem that Sajeev Arora has been explored several years ago. And the basic idea here is that, so we use a deep, so here we want to reconstruct a low rank matrix where the rank is much smaller than the ambient dimension from a few measurements of such a matrix, right? And so the way to do this is by using a deep linear network to approximate this low rank underlying low rank matrix, and this omega is the observation index. And if omega is or1, right, then this is just a simple, even simpler deep matrix factorization problem. And if the layer is equal to 2, and this is a kind of a Barrero-Montero type of factorization approach, right? This is a lot of previous study in the last decades. They studied kind of non-convex problems for solving this kind of a low-rank matrix recovery problems. But here we are considering an even deeper factorization. We consider L is larger than 2, right? We consider, for example, L equal to 3. So why do you consider like a deeper network? Actually, the depths and the width actually has a lot of benefits in solving such a problem. And for low-rank matrix factorization, right? Typically the rank we don't know, right? We overestimate the rank. And then when you overestimate, you enter the overparameterization regime, right? And here this plot shows you the benefits of the depths, where if you're increasing your overparameterization, right? If you use a two-layer factorization, you will overfit, right? The reconstruction actually error will be increased, that you are overfitting. But surprisingly, if you're using a three-layer network, right? And actually this kind of three-layer, the depth, it introduces kind of a bias towards low-rank solutions that it prevents overfitting, that the solution you get doesn't overfit if you use a three-layer network. On the other hand, so if you're using three-layer and you're increasing the width of your network, you can see that it can lead to faster convergence in terms of number of iterations, right? If you're increasing the width, so the width actually helps with your optimization landscape, and then the number of iterations you needed to converge to the solution will be reduced. However, if you're doing this kind of overparameterization, you increase the depth, increasing the width, you are increasing more number of parameters, right? Having more parameters means that the computation will be increased, right? It will be kind of expensive to solve this kind of overparameterized, to learn the overparameterized models, right? So here we can use we can show that actually we can achieve the best of two worlds in terms of generalization performance and the efficiency by exploring this kind of low-dimensional learning dynamics in this problem setting. And here we consider an even simpler problem, that we get rid of this kind of observation, this omega, and reduce the problem to an even simpler deep matrix factorization problem as a starting point to look at how can we achieve this. So basically we assume omega is R1 matrix. And for this, because we know that from a previous theorem, the previous section, we show that actually the weights is only happening within an invariant subspace, right? And we can do a decomposition based on a theorem to decompose the weights into a form like this, right? And by expanding this structure, right? So this is basically we have two components. One is the components on the left, which is a compressed weights, and a residual part on the right. And if you use a small initialization, right, which means that the residual part is negligible, right? We can ignore this part, and the weights can be approximated by this compressed component, right? And then this essentially means that learning the whole weights is almost equivalent to learning a small 2R by 2R size of weights, right? And then the computation can be much reduced. And by doing so, we can see that actually, if you just optimize the compressed weights, so the compressed weights is here, which is size 2R by 2R, and you compare the learning dynamics of the original weights versus the compressed weights, right? You can see that the learning dynamics exactly matches. But if you see the time, it needs to be to optimize the weights, right? There's a significant improvement when we're minimizing the compressed weights versus the original weights, right? But the thing is that we just consider a toy problem of this deep matrix factorization. Can we extend this to the completion case? So the completion case, remember we have if you go back to somewhere, we have a nonlinear like this kind of observation matrix here, right? So the low rank structures doesn't exactly hold. And if you look at the learning dynamics, right? Just brute forcefully doing learning this compressed ways, the learning actually will be diverging. So this orange curve, this green curve is diverging from this blue curve. And it turns out actually we can fix this. And the reason that this doesn't work is because we are not updating this subspace left and right here. But if you update the small, the kind of small subspace on the left and right at the same time, you can fix this issue, right? And then you can solve this completion problem as well, using this kind of a compression idea. And we can still enjoy significant improvement in the learning, in the computation, and then we can achieve very good performance, even comparing to the classical optimization approach for solving like matrix completion, that we don't encounter overfitting, and we are also achieving very high quality solutions. But this is kind of classical problems, right? And then next, I want to conclude this section by talking how can we adapt such idea to fine-tuning language models or transformer type of models, right? So nowadays, I think for GPT type of models, the popular approach to fine-tune those models is this low-rank adaptation, right? LoRa. So the basic idea of LoRa when fine-tuning this weights in the transformers is that basically this W0, W0 is a pre-trained weight, right? Once you pre-train it, if you want to fine-tune on a downstream task, you just add two components, right? This WK2 and WK1, the intrinsic rank R is very low, right? And then you can save the parameters by just fine-tuning this added components, right? And this is a basic idea of low-rank LoRa, or this kind of low-rank adaptation, right? And this LoRa actually is very effective, right? If you just test on this vision task, actually you're using LoRa, you can save significant amount of parameters, but achieve comparable performance in terms compared to full model fine tuning, right? So this is a very effective approach. But the thing is that for LoRa, you need to choose the parameter R, right? The R is a hardware parameter, which is the intrinsic rank or this internal rank of your added weights, right? And how to choose this intrinsic rank R is art, right? People don't actually, there's not a very good systematic approach to choose R, right? And empirically, people just choose this R equal to 8, and it works pretty well. However, this doesn't work when you're fine-tuning your models on very limited data, right? When you're fine-tuning your model using a high rank on the limited data, you will still overfit, even you're using LoRa, right? And the idea to fix this is that we know that depth prevents overfitting, right? If you consider the matrix completion, deep matrix factorization or completion, we show that 3-layer prevents overfitting, right? So the idea here, instead of fine-tuning a 2-layer weights, so why not we fine-tuning 3-layer? But the thing is that if you add layers and you add wise, it will add the computation, right? You need to sacrifice for the memory and the computation. And to deal with this fine-tuning extra layers, we can use this kind of a compression idea for deep matrix completion, right? We can use this to compress our weights into a small subspace, such that actually the efficiency we can achieve is comparable to LoRa. And this is the result, right? So here, the x-axis is showing you the number of training examples, and the y-axis is showing you the performance, right? And our approach is called deep LoRa, and you can see that actually when you have limited samples, right? our methods by fine-tuning more layers actually is performing much better. And if you're increasing the number of rank, you can see that this deep LoRa is very robust to the number of rank, right? So if you increase the rank of vanilla LoRa, the performance will be dropping significantly. But if you're using the deep LoRa with more layers, right, actually the performance is robust to the rank you choose. Moreover, if you look at the rank, I mean the fine-tuned delta WK for vanilla LoRa, right, is always 8. But if you use this deep LoRa idea, you can see that actually the rank is adaptive. So for a lot of layers, actually the adapted rank is 0. There's only a few layers that actually the adapted rank is from 1 to 3 to 4, right? So you can find much lower rank when you use this kind of deep LoRa idea to fine-tuning your models. And this is more robust to the choice of your hyperparameter R, right? So this comparison dynamics, so here this is we show that how can we adapt this approach to fine-tuning language models. So I think this idea could also have potential. How can we like do low rank training from scratch of nonlinear network, but we don't have much success yet, so we are still exploring. Finally, I want to conclude, right? So in the final session, this morning session, we show that the representation and the weights, they are dual to each other, right? So if your representation have this kind of a progressive neural cloud structures, it must mean that your weights you learn also have this kind of low-dimensional structures as well, right? And this kind of low-dimensional structure in your weights can further improve your training and fine-tuning your models, right? And this is the references for this talk. So the deep LoRa idea is appearing in SML this year. So finally, I want to thank all the collaborators, and our morning session ends here. So the afternoon session will be resumed at 1:30. Yeah. Okay, thank you. Any questions? Yes.
I think I have a few questions. First is, you have defined a few matrix, which is like one is NC, which is the trace of the within class feature multiplied the cross between class feature, the shooting was that. And the other one is the trace the
Divided
by the trace, the other trace. I'm thinking about what's the difference between two matrices and yeah.
Yeah, I think there's a certain difference, but here, I mean, the reason we consider this is because it's very hard to consider the pseudo inverse in the NC1 metric. So the deviation here simplifies the analysis, right? So if you consider the pseudo inverse in the previous definition, it's very hard to do analysis, and that's why we simplified this. But I think the thing is that if you consider this pseudo inverse, right, it captures the discrimination of your features, right? It's not the between class covariance is not only acting as a normalization factor, but also captures the discrimination between classes. But here, our study here for this one, that if you're just using a trace as a normalization, it doesn't capture the discrimination of your features, and that's why we introduced a second measure of this feature discrimination. Yeah.
My second question is about the difference between a single layer linear network and multiple layers. So I think in one result we showed for multiple layer network, you have the assumption that it achieves the product, achieves the minimum known solution.
Right.
And if that is the case, why don't you just use a single layer which can also find the minimum known solution? And if that is the case, I think the performance would be the same.
Yeah, we test this. It seems like if you have more layers, so the performance, the test performance will get better. So my intuition is that if you have more layers, it's easier to train. I mean, here, I mean, if you look at this invariant structure, right? So every layer is approximately low rank, right? So the low rank is controlled by the proximate low rankness is controlled by your initialization, epsilon, right? If you have more layers, then you can, when you multiply the layer together, right, you can lead to more low rank or collapse, right?
Yes. If you have single layer, this matrix eventually will be highly ill conditioned.
Yes,
If
yes.
you have a
It's very hard to train, I think, in terms of optimization. Yeah. Yes.
I have a question. Do you think there's a relationship between the low rank and the inductive bias of neural network? Because I think the performance of the single value decomposition is similar to the inductive bias.
Yes, yes. I think there could be like a lot of relationship there. Yeah.
Yes, because you also say that low rank is also an implicit bias. I
Right.
think that this bias may be the same. They have the same.
Yes, you consider the frequency like a Fourier transform in the spectral domain.
Some research about this.
Yes.
Can I answer your question a little bit? So I mean, maybe the afternoon can mention this again, right? I have a slogan, right? The only inductive bias is compression. Data is dimensional, so that each layer has achieved compression of. So that's why there's slow dimensional of the right, and also that's only inductive bias, universal inductive bias. Okay. And I asked the Benjo many times, what is that inductive bias? We never answered that question. Now I figured it out. Right? Everybody just. The only thing that you're pursuing, representation wise or data structure wise, so each layer, those operators are expensive, so approximating some projection or compression. Okay. So either you take that into your design or add that into your model. Whatever you do, that's the only type of bias you should have.
Okay. Another.
In the case, so you showed that you have an equation d defines m equal to d minus 2 times r.
Oh, which slide?
So you say you need there are invariant subspaces which is a blank
Oh.
r. Then you need you will only change the gradient descent will only change to r.
Yes.
And I wonder, so in the formulation, what prevents us to just select d equal to r so that rho of t doesn't appear at all? M is equal to 0.
So you mean why not? I mean, I couldn't quite get your question. So do you mean that why not the subspaces of dimension r instead of 2r?
Control the width and the depth of the network. For example, we set the width to be d equal to 2r. So m, in this case, m is equal to 0.
Oh, yeah, I see.
And then the network is smaller and
but the Ys actually also helps. I mean, the depth, the Ys actually helps to accelerate your convergence. Actually, we try this narrow network. It's size 2r. And we find that actually the computation time with using these compressed weights versus using a narrow network, the computation time still have some benefits. Yeah.
This comes to my next question. So the experiment suggested that wider networks are easier to train. But I'm thinking of a very simple situation where you have a single layer, you have a linear regression problem, and then you have if you are the problem is underparameterized, it would be somehow strongly convex. It has a linear convergence rate, and if you overparameterize, the problem is no longer strongly convex.
I see.
Convex. So the convergence rate, I'm thinking that it will be slower. So what's the intuition? How do you explain?
I think if you're near one of the global minimizers, still you can have a local linear convergence. But if your initialization here, actually you need to use if you're using initialization very small, the initial convergence will be very slow. There's some trade-offs there. And I think the benefits here is that the depth and overparameterization can help the preventing overfitting. Yeah, to enter parameters, you could encounter like poor generalization performance. Yeah. Okay. Okay, so this is the end of morning section, and we will resume at 1:30. Thank you, everyone.
Cool. And I'm going, here is the outlines for this afternoon's session. Since before this session, the first lecture, Yi talked about how to measure the goodness of low dimensional, measure the goodness of data in the high dimensional space using the principle of like lossy data compression. And now in this lecture, I will talk about like how can we derive certain kind of neural network architectures, but from more like unrolling optimization perspective. And after this talk, the next lecture, Sam will talk about like the last lecture about how can we build a white box, building leveraging the first part, which is the learning objective, plus the unrolling optimization. How can we derive the white box transformer architecture that has some interesting like scalable and interesting behaviors in the final final session. Cool. Let's get started on this unrolling optimization part. So just a brief recap of the materials of the previous lecture and the lectures in the morning. Like a very simple, like a basic setup of this whole tutorial of the low dimensional structure. One simple setup is about this linear structure. So basically, here you have like a fat matrix A, and here you also have a like a low dimensional like vector, which is here we assume Z is sparse. And what you can observe is you can observe the X like, and then you want to solve an inverse problem, try to recover or try to identify what's the low dimensional structure, which is identifying the Z. So here the problem is it looks like pretty simple, which is a linear, is more like a linear generative model, and you want to given the X, you want to find what the Z is. And I think and the previous lecture is what Yi talked about is for the actual like real world problems probably is not like generated as simple as a linear model. So here you actually have some now complicated multi-mode like nonlinear structures in the real data, and you want to measure the goodness of the representations in this more complicated like high dimensional space. And here you can use lossy data compression to measure the goodness of the representations. And you can also slowly transform, here is slowly transform from the nonlinear manifold through a function like f, transform it to a more structured and compact space, which is like orthogonal linear subspaces. And those are for this setup. And a little bit motivation on why we want a white box model, given existing the success of the deep learnings. So one big success of the current practice is about the scaling loss. So here is a nice paper from OpenAI. Given on the x-axis, as you increase the number of compute, you can identify a parallel, like the test loss follows a parallel decay with respect to the number of compute. And in the middle figure is like the data set size, and on the right-hand side is the number of parameters. So if you plot this in a log-log scale, it follows a parallel decay. So which means that for certain problems, you can expect that as you have more compute and as you have more data, then eventually the performance will improve in the future, which means that certain problems can get mitigated or get partially solved as you increase the model size or the data size. But however, as by the way, here is scaling law for a large language model. However, as is very successful, say we saw this scaling law behavior, but there's a lot of stuff we don't understand what's going on inside of the model. For example, there's on the top right on this image figure. So this is a figure from like Dino paper. What they found is if you use a self-supervised learning model, like you use a SSL approach called Dino, and you train it with a vision transformer, then you can saw an emergence of segmentations happening inside of the model. So basically, this is the heat map of the Dino inside of the vision transformer trained by Dino. And you can find like the model is like segmenting the object in front of the image. But they show that if you train with a vision transformer with a supervised learning like approach, it does not show up such segmentation map. And similarly, like on the bottom, like right, you can find like people in the NLP domain, what they found is if you give more like demonstration samples in the prompt, then the model could learn this relationship and apply this during the test time. So you don't need to train the model, just apply this called in-context learning, and you can do predictions, apply this function you learned from in-context, and then apply it to a test data point. So basically, there's some interesting emerging behaviors happening inside of these large models. But given the models are like empirically designed, it's hard to understand what's going on inside and why this kind of phenomenon happens at the first place. So in this lecture, we'll provide an alternative perspective of understanding what each layer is doing from an unrolling optimization perspective, and try to construct the networks such that every layer we kind of understand what's the learning objective or what's the design goal of this particular layer. And then we show it by like layer by layer, we try to transform this more complicated like submanifolds to a like mixture of linear subspaces structure. So that's over like basically we are using the deep networks to achieve certain goals, and we define those goals at the first place. Okay, and so here is a slogan of like a very high level overview of this lecture. So basically, suppose we have some like on the left-hand side is the X, the observations or the real data. On the right-hand side, we call it a representation or like the hidden variables we saw before. And we consider two cases in this lecture. So the simplest possible case is what we saw before of this linear case, that this G map from right-hand side to the left is realized by a linear mapping. And for the second case, you can view this linear case more like a warm-up case, which we demonstrate like how can we construct a simple neural network from this linear case. And then the next case we'll show is the nonlinear case, which is this G map is more complicated or is beyond the linear case as we saw for in the first case. And then we will show how can we construct this encoder mapping step by step, try to incrementally to try to linearize the representation at every layer. Okay, so that finished the first part of the background. And now I give an overview of what like a very high level idea of what unrolling optimization like is for architecture design. And then afterwards, I will show two instantiations of this unrolling optimization. The first case is the E-star network. I think E and talk about in the previous slides, previous lecture of earlier work from Yang LeQuin's group, like how can we use sparse coding to construct or design a network to solve sparse coding. And the second one is how can we do similar like unrolling optimization using the principle of lossy data compression and to step by step try to linearize the representations at using a nonlinear mapping constructed from an unrolling optimization approach. Okay, here is a very high level overview, but I hope folks could like get some high level ideas from this figure. So consider, because for the deep neural networks, it has multiple layers. So usually it's not like it's not just a single layer. People demonstrated like the deeper the network is, the more like a performant the model is. Usually people would use multiple layers. And at this lecture, we are showing like what's the purpose or what's the goal of each layer. So suppose at the else layer, we denote the representation as like ZL. which is a d-dimensional vector. And here we have a block L or a layer L at the right-hand side. And then after this layer of mapping, we got the output, which is a ZL plus 1. And the question is, what is being improved or what is being optimized after this layer of transformation? And there's different ways to approach this problem. And the way, like the approach we are going to introduce in this lecture is more from a bottom-up approach. So basically, you first define what's the goodness or what kind of properties you want to improve through this layer of transformation. Say here you have a loss function like this L. You plug this representation Z into this loss function L, and you say, hey, I want to optimize this objective through a nonlinear mapping. And after what you want to achieve is you want to optimize this L of Z. And through a bottom-up approach, suppose you can directly perform like a gradient descent over this loss function, like one step of gradient descent. And then as the step size, like under certain conditions, you should be able to decrease your objective through like one gradient descent update, which is on the bottom right, bottom up side, like this visualization. So here you use L as a goodness measure to measure how good this representation is. And then how can we design such a layer to achieve this goal? So basically you can think there's a way like this unrolling optimization is after a forward mapping of this layer, it is equivalent to perform a gradient descent approach on the representation. So basically the layer is optimizing the representation through a gradient descent or through a certain optimization procedure, and which makes the representation becomes better. And there's different ingredients of this unrolling optimization approach, as you can see from here. Like one component is how can you define this gradient descent, or because also in optimization literature, there's different types of optimization strategies you can play to decrease your loss function. And here in this lecture, we mainly play with or use the gradient descent as like one approach to design the architecture. And another ingredient is this learning objective. So there's different kinds of like goodness measures you want to improve, or you want for this particular like representation vectors. What kind of learning objective you want to plug in this gradient descent? Because as you can imagine, like if you replace the L with another L, it would like lead to a different architecture to implement your gradient descent. And like at the very beginning, like is how do you like model your signal, which also influence what kind of objective you want. Suppose your signal, you assume this X is generated through like a linear mapping from Z, then you probably use this least like sparse coding related approach to like define your learning objective. And suppose your signal is generated or through a nonlinear mapping, you probably want to use a different like learning objective afterwards. So overall, that's like a very high level overview of what the unrolling optimization is. So if you like forgot the whole lecture, you can what you can the takeaway is one layer as an optimization step to like improve your representation. So hopefully that's that could be helpful. Okay, and the next I will introduce how can we use this unrolling optimization approach to design a simplest, like through this linear generated model setup, what kind of like network we can construct through like a sparse coding approach, like which is designed through unrolled optimization. Okay, as we saw like this figure several times in today's tutorial, so given this observation X, this X is generated by A multiplied with Z. Like Z is some unknown like vector, but we know that Z is sparse, or Z has low dimension, has a certain low dimensional structure. And what we observe is X, and like we start with a very simple case is we know exactly what A is. And then you can solve like an inverse problem, like given X and A, how can we identify or recover what Z is? You can view Z as an encoding or a more compact representation of the observation of X. Here is a diagram I copied from a paper from Chen et al. Like basically from the left, you observe this X, you can go through multiple layers of mapping, and then you can output a Z, and the Z is close to the actual Z in the linear setup. So basically, after multi-layers of mapping, and we will introduce what this layer is, and through this mapping, you can recover the ground truth of Z. And just a brief review of what this sparse setup is. So a sparse vector is in the middle, so basically it has very few non-zero entries. And on the left is dense vector, and on the right-hand side is a sparse vector plus certain kind of noise. And what we measure, like one way to measure the sparsity is using the L0 norm, basically counting how many non-zero elements in this vector, which is defined here. And one way to one common approach to do sparse recovery or sparse coding is do a convex relaxation of this L0 norm using a L1 norm, which is the formulation written down here. So here we know X is the observation, and we consider the case that we know what exactly A is. And we want to found a Z, which is the sparse vector, such that after multiplying A with Z, we can reconstruct what X is. And in the meantime, we want to minimize the sparsity or the L1 norm of the Z vector. So this is the like one formulation you can do to do this sparse coding or sparse recovery problem. Given this formula, you can do a like Lagrangian relaxation that solve a easier problem or a unconstrained problem, which is you basically is a lasso problem, like a square loss with the L1 regularization. So basically here you want to minimize over Z such that Z can reconstruct X, as well as Z is the Z has a smallest L1 norm. Just want to make some very high level connections to the first of all, this is a very classical problem in the literature of compressed sensing, sparse coding, dictionary learning community. Has been there for a long history. And I want to connect to certain recent problems happening in the in those recent hot very popular companies from OpenAI and Anthropic. So basically, what we found recently is sparse coding and dictionary learning can be a very scalable approach to do interpretability of large language models. So what they did is, so basically almost the same formulation, but they kind of not necessarily very rigorous dictionary learning problem, but they want to found dictionaries such that they want to decompose the representations inside of large language model, and then they want to decouple or learn monosemantic concept from these representations. But overall, you can think as using a dictionary learning approach. And what they found is what's promising is this whole pipeline can be pretty scalable, which also attribute to the previous practice from dictionary learning community, that you can actually recover or learn these concept dictionaries and try to interpret the model predictions pretty well. So just a very high level connection that the dictionary learning could also be very useful in the large language model community. Okay, so then given this objective, how can we design a network to learn the representations or to recover Z? So here we know what the learning objective is. So you can think this whole term, these two terms together is defined as the L of Z, so which is the learning objective. And the first thing we can do to do this unrolling is you first compute what is the gradient over this objective. So here we are taking a proximal gradient descent approach. So here, the lambda of z of L1 is the like regularization term. We first compute the gradient over the first like least square term. The gradient is defined as this is like A transpose multiplied with the residual term. And what you can do is you first perform a gradient descent, following the gradient descent to get a z hat of k. Like k, you can think as the kth number of layer. And after this z hat, you want to deal with this like L1 regularization term, which the definition, or you can view this as an activation, which is given this z hat, you want to do a self-thresholding to this updated vector, and then you can get the updated representation, which is zk plus 1. So this two steps of mapping consist of the whole one step of proximal gradient descent update for solving this lasso problem. And just to try to make it more visually more friendly, on the bottom right, which is the visualization of the self-thresholding. So if you ignore the very left, if you put all the activation on the left-hand side as 0, so it's very similar to the ReLU activation with a shift. So basically, this on the bottom right, this activation is exactly the update step of this sign composite with this max operator. So basically, you can think even the problem itself is like linear, but when you want to solve this problem, you need to apply a certain nonlinear activations or nonlinear operations to actually solve this simple linear problem. And just try to make it more looks more like a deep neural network. So here, if we arrange these two terms together, then we have this single update, which is given the x, we want to update the whole thing. And okay, there's a typo here. Sorry, that this should be z. So this x should be z and the y should be x. Sorry about that. So we want to update like this. And here's you can think as a linear map, and then go through an activation function, which is sigma lambda. And then you can get the next iterations update. And to make it more looks, sorry, the typo's still there. To make it looks more like a deep neural network, here's a diagram I draw on the right-hand side. So basically, given the case iteration of z, you go through a linear mapping, which is W2. W2 is defined by the A matrix. And then given this, you also need another input, which is the original signal x multiplied with another matrix. And there's also a residual connection from z, there's another residual connection from zk to aggregate things together. And then you go through a nonlinear activation, and then you got the output. So this is one layer of transformation that which is exactly equivalent to a proximal gradient descent to solve a lasso problem. Here, by the way, the dictionary, we assume A is given, or we know what A is. And just go back to the very high level diagram I showed in the beginning. Here, suppose given a sparse coding objective, if we do a gradient descent, then we can unroll an algorithm this architecture could looks like this. So basically is a E-star or iterative self-thresholding mapping, which looks it's a more structured MLP, I would say. Basically as a linear mapping plus a nonlinear activation. So if we stack things together, so suppose the previous showed example is just a one step of E-star. And if we stack this E-star together, is equivalent to do multiple steps of proximal gradient descent. And eventually, given our knowledge of optimization, if you put enough number of steps, then you can solve this problem and obtain the optimal solution for this lasso problem. But here still, we still need to know what the A matrix is. Basically, you need to know the dictionary. But what if the A is unknown? You just know what the observation is, and you don't know what the dictionary is, which is actually the case for the ML, all the large language model interpretability. So basically, what they can observe is the representations inside of the large language model, but you don't know what that dictionary is. You need to identify those concept dictionaries. So what if dictionary is unknown? So there's a whole literature called dictionary learning, which is another DL for short. So basically you need to identify what the right dictionary is, and then you use this dictionary to sparsify or to reconstruct your input. So very high level, like or like another way you can think of this is if we go through from Z0 through this mapping to get ZL, this forward mapping is equivalent to solving multiple steps of gradient descent. But in the end, you still, then how can you update this A? Like, because you don't know what A is, then you can use, this is the previous set is what I said is corresponding to the forward mapping. But then what if A is unknown? Then you can do back propagation. Like suppose you use ZL to do certain like supervision, use some other loss to put ZL into a loss, and then you do a back propagation as used in the standard deep learning. Okay, so this is you use in the deep learning like standard pipeline, and then you can update the A like accordingly. So basically, you can use standard back propagation to update the A. But here you need to distinguish what the forward and backward is. The forward is given A, you want to learn or you want to optimize the representation. But the backward propagation is you want to learn what the dictionary you want to be like sparsify against with. So that's kind of a very high level concept of the distinguish what the forward and backward. And just going back so as we saw here, every layer we are using the A as a single dictionary. So we are using multiple steps of proximal gradient descent to solve the sparse signal. Here we are like all the A's across, you can think all the parameters across all the layers are shared across each other. So what if we untie, like not make these all the ways shared with each other, just one dictionary for one layer. And this eventually goes to this Jan's earlier work on like every layer, every A is learnable. This is more similar to the standard practice of deep learning. So every A is kind of a learnable parameter. But still, like if you compare this with a standard like generic MLP network, this one is more structured in the sense that even if all the A's are untied, but you can think like every mapping at least is corresponding to an optimization step to solve a dictionary learning problem, which has a more like interpretable, you can interpret or you can understand this mapping much better like than a generic MLP. So yeah, there's a whole literature on like this unrolling using the sparsity. So basically you can extend this sparse coding to the convolution case. You can this corresponding to the multiple layer of convolutional sparse coding networks. And also recently people like also some work from East group also, like you can actually push the performance of such like sparse coding like ESTA type of convolution networks to in real world problems, and you can get decent like performance using such like structured networks. In particular, if your image is corrupted, what they found is the sparse coding layer is much more robust against those noise, like under like you can call this noisy, like is a distribution shift. And if you use this sparse coding layer, you can denoise against those noise during the test time. Okay, so that wraps up like how we design this sparse coding layer, like in this linear case. Next, we'll go to like how suppose the signal is more non-linear. How can we like use like unroll objective to slowly or iteratively to linearize the representations through nonlinear mappings. So here is a visualization of just like suppose that your signal is nonlinear, And the high level goal is we want to do an incremental step. Like suppose we realize a mapping like to learn the representation, to slowly improve the representation from ZL to ZL plus 1. Then in this case, we want to further or slowly make it more linearized compared to the left-hand side. So that's a very high-level goal of this part. Okay, just a brief recap. So here, suppose the original signal is lying in a mixture of low-dimensional submanifold, but overall the data is intrinsically like in the low-dimensional, like has low-dimensional structure. And then our goal is we want to found or we want to construct F such that we can map these like non-linear manifold to a more structured like to a space that is more structured in the sense that like different classes, they are like in the same subspace, and different subspaces, they are orthogonal to each other. So basically we want to compress and linearize the representations through a mapping, which is F. And we'll show how we can reconstruct this F. As in the previous lecture, he talked about like how can we measure the goodness of the representations using this lossy data compression technique. So here just a very brief recap. So overall, we want to increase or we want to maximize the information gain through this computable measurement, which is this log determinant term. And in a very high level, like we want to expand the representations like as a whole. Like if we put all the representations together, we want to make it more as diverse as possible. And on the right-hand side is the compression term. So basically, if you collect all the representations from the same class, we want to compress them as much as possible. And in the end, what you can get is suppose S corresponding to samples from or representations from the same class. So basically you compress the representations from the same class to a very low dimensional linear subspace. But overall different linear subspaces, they are orthogonal, then you can maximize the number of blue balls in this case, which also maximize the information gain. So basically locally want like similar objects or similar representations, you want to compress them as much as possible, but you also want to make your representations to be diverse. Diverse means like orthogonal in this case. Okay, and then if we go back to our previous like a very high level picture, which is given the objective, then you can do unrolling optimization to construct this particular map. So then now our learning objective changed from this sparse coding objective, which is square like L1 regularized the square loss, to another loss, which is the lossy data compression loss. Then a simple idea, as we show in the very early diagram, is we can perform a gradient descent approach to improve this objective for these representations, and then we can make it like we can parameterize this as a mapping or as a layer. Here, just a minor difference is all our previous like slides are about like minimize certain learning objective, but here the objective is maximizing this objective. So correspondingly, here, instead of doing gradient descent, we are doing gradient ascent. So basically you can put a minus sign to the learning objective and also to the update. So basically here, what essentially is changing from the previous part is we change another learning objective, and we want to see how the architecture changed accordingly. Okay, so then still similar to the previous sparse coding part. So what we need to do is we want to look at, or we want to calculate what the gradient looks like in this particular case. So previously is a very simple like square loss is basically like a machine learning 101. You can compute that directly. So here you need look at like probably the matrix cookbook to look at how to compute this log determinant derivative. But overall, you can think is just apply like the chain rule, and then you can found like you can derive or you can compute what the gradient over these two terms are. So overall is there's involving some like matrix inversion, and then apply this inverted matrix to the particular like ZL at the else layer. But in particular, a difference compared to the previous, like all the previous like presentations is here, we actually need certain labels for this particular mapping. So all the E and all the C matrices you can directly compute. But for the pi, I will show how can we approximate this pi through a forward mapping. But overall, you can think here we change another loss and we compute the gradient accordingly. And then we want to parameterize a layer to implement this like projected gradient ascent. Like another interpretation of this particular gradient, like the equation 3, what does this actually, what's the geometric like meaning or interpretation of this EL is quite nice in the sense that if you do a self-regression over all the representations with itself, so basically given a representation ZL, you want to use all the current representations as a matrix Z, you want to use the linear combinations of all the representations to reconstruct ZL. It's more like a self-regression. And in this case, what the E matrix is the residual between the ZL and the reconstructed ZL. And is actually like the residual against the subspace. And if you plus this residual, is it like make it more like separate or more diverse, is corresponding to the E matrix, which actually corresponding to the expansion. But if you like follow this direction, a minus C is corresponding to a compression and make the overall volume smaller. So here is like more geometric, like kind of realization of what this kind of mapping is doing is given the current else layer, you can follow this gradient descent, then it slowly makes the data more linearized in the similar to the earlier like slides we saw here. So basically it want to achieve certain configurations as in this like particular figure. But a challenging part is to implement this gradient descent, you need to know what the label is for every ZL. Suppose you are like for the training data, you know exactly what the training label is for every sample, but you need to apply this mapping to a test sample. And for the test sample, you don't know the label. If you know, you don't need to test. So in this case, we need to estimate what the pi is. So essentially is this mapping is very well defined except for this pi term. So the E matrix and the C matrix, you can compute it from the training data to solve like a matrix inverse problem. But for the pi, you need to estimate what's the probability of this particular sample belongs to the J's class. And interesting, what we found is you can do a very rough estimation of the membership or the label from the data. So basically, because we have a clear estimate, clear understanding what the same matrix is. The same matrix is corresponding to the subspaces spanned by the J's class. So what we do is like basically we do like a softmax approach to approximate how can we like what's the probability of ZL belonging to the J's class, and that's how we estimate this pi of hat. Suppose this we have the oracle or we have the actual like underlying ground truth like pi of ZL, then this exactly corresponding to a like the ground truth gradient. But if we plug in this estimated pi, this is the approximate gradient of the original like lossy compression objective. So the resulting architecture looks something like this. So here we have an E term, which is corresponding to the expansion, and we have a bunch of C terms corresponding to the compression for every class. So here we have a class from 1 to K. And then we have like a sigma, which is a nonlinear activation, what we define as here. Basically, you can think as a softmax like a softmax operation. And the diagram looks something like this. So you this is the equation 21 is corresponding to a gradient ascent. So what's the ingredients of, or what's the different components of this gradient ascent? First, you have a residual connection here. And then you have an expansion term denoted by this E of L. And then you have another branch, which is you have multiple multiple compression matrices corresponding to different classes, and you multiply with ZL with all these like C matrices, and then you aggregate the output through like a softmax approximation, and then you aggregate the three ingredients together for this equation of 21, and then you got the you do a like projection, which is normalize all the z's to a sphere, and then this consists of this else block. So basically, the else block is mimicking or implementing approximate gradient ascent to solving this lossy data compression objective. So back to the very high level picture I showed very early. So previously, given this sparse coding objective, we unroll like a Lista object or a Lista network. Here, if we change the objective to a compression term, then we have a different like architecture, which is you can exactly compute it from you can derive the architecture from the objective, and you can unroll this objective and you can derive this, you have this nice, like interestingly looking architecture on the right-hand side. And here are a bunch of a few connections to some existing architectures between the RedDoNet, which is the network corresponding to this lossy data compression, versus the existing architectures. So, so first of all, it has a residual connection, which is similar to the residual connect. Also, ESTA actually also has a residual connection, but the residual connection is before the activation. Here is shares certain similarities as residual networks, and also it shares certain similarities as a ResNext network. So basically, there's multiple like branches inside of this else layer, where we also have this multiple branches. Like every branch is corresponding to a compression against a one subspace in this case. And another like difference or interesting part is different from the existing architecture. In this case, we can actually compute or to derive the model parameters without backpropagation. So as we saw earlier, like here we know exactly what the E matrix and the C matrix are. So how you can compute that is you have all the representations at the else layer, and then you can compute this E matrix basically from data. You don't need to do backpropagation to actually find what the E matrix is. So essentially, you just do a forward mapping to construct the else layers, all the parameters you can compute like from like through a forward only mapping. You don't need to do backpropagation, which is quite interesting from a more conceptual perspective. And also, there's another like connection to a mixture of expert like examples or realizations of all the existing MOE architectures. So here, the interpretation of mixture of expert in this context is basically how can we estimate the membership of ZL, or what's the probability of ZL belonging to the JS class? Then there's a very high-level connection between this branch, which is we show here, versus the existing MOE architectures, like which is also seems like be a key gradient for scaling up large language models recently. Here now I show some like figures or visualizations of whether this RedDo network actually could compress the representations over the layers. So we start with a very simple example. On the first row is here we have a mixture of Gaussians normalized to unit spheres in this two-dimensional case. And now we can construct 2,000 layers of RedDoNet. The reason that we can construct 2,000 like layers is we don't need to do backpropagation. We can construct this by gradient. You can think we are doing gradient descent. Then we can construct as many as layers as we want. Like then we have 2,000 layers here. And on the right-hand side, we are showing the loss functions or what's the learning objective is changing over the number of layers, or you can think as number of iterations. And from the left to the middle is a 2000 layers of mapping. Then we can compress all the representations from the same class to a point. And also the 2 points or the two sets of representations from different classes, they're also orthogonal to each other. It's corresponding to a very early on what we shown very early on the right-hand side optimal configuration is you have orthogonal like subspaces corresponding to different classes. And also we also try this on a slightly more challenging case, which is increase the dimension to by 1, and we have 3 clusters in this case. And then if we perform like same like 2000 layers of transformation, then we saw similar stuff. So basically all the points from the same class, they are collapsed to a point. And also the directions or the subspaces spanned by the 3 classes, they're orthogonal to each other. So which also corresponding to our optimal configuration we saw earlier. And interestingly, through this kind of white box unrolling idea, as we saw before, if we can actually derive the convolution operations by looking at the gradient of this lossy data compression objective. What does that mean is previously what we did is we collecting all the samples from the same class. So basically here, for the same matrix, this ZL multiplied with pi j and then ZL transpose, you can think we are computing the empirical covariance matrix by collecting all the Z's from the same class. Basically, you can think we are compressing all the samples from the same class. But what if, what if we have certain domain knowledge that we know that the class label will not change if we shift this image to certain, like on the x-axis or on the y-axis, then we can collecting all the samples from the same class, and also it's all is like augmentations what we defined in as a prior, like say either rotation or like cyclic translation. We basically put all the zeros we have in the training data set, and also all the augmentations of this zero together in this training data set. You can think we are augmenting all the Z's by its like this invariant assumptions that we can augment all the training samples, and we put them together and we derive what the gradient looks like in this particular case. Then we can actually like derive the convolution operations in this case by only looking at the gradient. So basically all the, like previously we have an E matrix, which is in the vector case, is a inverse of a regularized covariance matrix. And in this case is corresponding if we augment all the Z's by its corresponding like augmentations or like invariant augmentations, then in this case, we can actually, this E matrix is corresponding a convolution operation in this case. Due to the time limit, I cannot go into detail for this. This is a very interesting observation we saw before, and corresponding to what E said earlier, like in the deep learning literature, you have multiple channel like convolutions, which is slightly different from the signal processing literature. So here we have some nice like derivations that you can actually derive from first principle that corresponding to this multi-channel convolution like operators by like augmenting the samples and computing the gradient and see what the architecture looks like. Okay, and in this case, we can actually like, suppose we compare the invariance of the ReduNet versus the ReduNet by this convolution, like considering the invariant perspective of the previous derivation, then in this case, we can achieve very good test performance under like this shifted like versions. So basically, you can actually design such like networks by only forward propagation or forward constructing networks and be invariant to different like kind of shift versions of the sample. Cool, and that wraps up the ReduNet, or how can we unroll lossy data compression objective and derive what the architecture. And then I give a very brief summary of this unrolling part. So basically, the very high level idea is instead of trial and error and try to do some like search or using certain intuitions to design the network, you can actually design the network from a different perspective. So I'm not arguing this is the only perspective or only approach to design the network, but at least you can use this perspective to provide more insights, or you can using the knowledge or the principles you know in the classical literature and then design such networks. So basically, instead of trial and error, we can use this unrolling optimization. And also, instead of doing back propagation, it is possible to do forward propagation only, because I think from certain some neuroscientists like they argue that for in the brain it's very hard. They don't know what the back propagation is, but there's definitely a forward propagation. So is it possible to like do this like network training by forward only? That's an interesting conceptual and probably a practical problem. And for interpretability is really nice in this sense that you can know, because you design this from principle that you know what's the geometric or statistical property of every layer designed through this way, and it makes this whole layer or this whole network more interpretable than a black box trained network. So hopefully this could be helpful to some extent. And just to go back to the very high level picture I showed in the very beginning, like here we have 3 ingredients and then every layer designed as an optimization procedure, and we are optimizing certain properties measured by this loss function. And if we unroll a linear, under this linear setup, if we unroll a sparse coding objective, we got this ESTA. And if we unroll a lossy data compression objective, we got a redo net. And in the next lecture, Sam will introduce how can we design a white box transformer architecture, which is a transformer-like architecture, but is not exactly the same as a transformer. So if we look at these 3 ingredients, what was the difference? What are the differences? One is, so in the whole lecture, I'm using like one vector to model one signal, or use one vector to model one like sample. So what if, so inspired by the practice, what if we model this sample by a set of vectors? So basically, instead of modeling it as a vector, we model it as a set of tokens or a set of vectors. And in this case, we can, like, this will change how we model the signal of Z. So basically, you have a set of tokens to represent one sample. And also, like, how can we make this unrolling optimization more efficient in the case that we can scale up this model to a very large scale? So that wraps up my presentation. Thanks, everyone. Yeah. Any questions?
Thinking this framework by the network, the thinking as an iterative optimization.
Okay. I think this the advantage is what I summarized in this slides. But overall, like one advantage is through this way, you know, this layer is optimizing, at least you know what's the learning objective, what kind of objective this layer is optimizing. So in this case, for example, if you go back to the very early on, like if we go back to the lista setup, so you know like what's the like mapping looks like, and under certain conditions, you know all kinds of properties of this mapping. Like say it's contractive, it's doing a certain kind of denoising against the certain subspaces. You know, like the meaning of every parameter or every set of parameters in your model. I think that's the difference. Yeah, yeah.
Yeah, I think there are sense. So why do we call it a network? Just people name it. Oh.
We just know how many names are given to the something complicated players. Very hard to that. How do the work system modify that?
Yeah, I think basically in the next slide, in the next lecture, in a nutshell, so you can construct such mapping without knowing the number of classes, and then you can identify the different set of subspaces and construct the network accordingly. Yeah, there's we did some recent extensions to exactly solve the problem you said. Yeah, yeah. Thanks for the question.
Basically, that's not very important representation. It's also like the first one to remember is Gaussian. So after learning all these, do you ever test Gaussian?
Yeah. So basically, we are not. First of all, that's the next question, and what we are assuming is now we are not assuming like we have certain Gaussianness in the original input. The Gaussian, or you can compute the log determinant in closed form only if it is Gaussian. You can think we are assuming the optimal, like we know exactly the optimal like configurations of this representation will be like mixture of low dimensional Gaussian in this case. And what we are doing is we are using the Gaussian to like approximate this like mixture of Gaussian to approximate every layer. And then we try to improve the representations using this objective. Yeah. So basically, eventually what we got is probably this figure could be helpful. So here, so we have 2,000 samples, and every like 200 samples is from the same class, and we want to compress all the samples from the same class to a like linear subspace. And what we can find is after going through this transformations, like samples from different classes, they are orthogonal to each other. So this is the like feature realizations we're doing in this particular case. So basically, they have this mixed, like orthogonal mixture of subspaces structure. So basically, samples from different classes, if you do this inner product, they are orthogonal to each other. So back to your question. So the optimal configuration would satisfy what we assumed in the beginning. Yeah. Does that make sense? Or yeah. Yeah, it is. Yeah, the short answer. Yeah.
Yeah, you do the reverse and you do
Yeah, that's something I think also other folks in E's group also did. Basically, what we introduced today is from X to Z, and we have some work from like we can learn this representation through this like ReduNet or maximal coding rate reduction approach to learn the linear subspaces, and then you can go from the linear subspace back to X, and they have some works from E's group like have this. Exactly, I think pretty similar to what you said. Yeah.
Your work actually presented feedback. So that you good question is that the way to really help is an optimization to learn other people make it besides you or the back. so that the S is not the equivalent, it's the one that, that's the late. The sample at the equivalent S will go back. The sample the subspace.
So if you modify the mapping matrix in different layers, so in the network, you need to be grateful
Yeah, as I said, like even if you untie every layer, you can think at least it's doing one step of gradient descent against that particular dictionary. So if you that's how I call it interpretable. If you think this is interpretable, then it's interpretable. If you think it's not interpretable, then that's fine. Yeah. You can think you are using a different you are using different sets of dictionaries at every layer. So at this particular layer, maybe this particular set of dictionary is like more like optimal than like using a fixed dictionary, something like that. And also for context, there's also a more theoretical work on this unrolling literature. So basically what they've shown is there's a benefit of untie all the weights across layers that you can get probably faster convergence rate compared to like you are using a shared like dictionary. So there's some theoretical understandings of this untied unrolling approach. Yeah. Oh, sorry. Can you yeah, sorry. I see. Yeah, that I think in terms of convergence rate, as I said to the previous question, like there's certain like if you like allow certain flexibilities in the like weight sharing mechanism, you probably got the like probably even better convergence rate for solving certain like problems or solving certain inverse problems. There's certain literature on that. I'm not sure whether that's related, but we can talk offline if you're interested. Sorry. Yeah.
It's about that we only do finite steps, right? We cut off the obligation you can do. But here then just like, just don't take
All right, okay, let's get started. So welcome to the last lecture session of the day. I'm Sam Buchanan. I'm going to be closing things out for us here. I'm going to talk sort of proceeding on from the previous lectures, so we've identified compression as a really useful principle and also kind of a measurable quantity for kind of identifying and transforming low-dimensional structures in high-dimensional data in the last two lectures. And we've shown sort of at a basic level how we can turn that into a neural network that actually transforms general high-dimensional distributions, low-dimensional distributions in high-dimensional data towards more structured representations. So that's what Yi and Yaodong have just talked about. And now I'm going to talk about how to kind of adjust things just a little bit so that this can be scaled up and made very practical. And I'll talk a lot about experimental results that we see when we do that, interpretability benefits, and a few future directions as well. And don't go anywhere after this lecture. So we're going to have a panel session with some great folks at 5 p.m. So that'll happen after a short break after I'm done with this lecture. So before I'm going to pick up right where Yaodong left off. But before I do it, let me zoom out very slightly and just talk a little bit again about some of the motivation here. So all throughout this tutorial, we've been talking about kind of low-dimensional structures, high-dimensional data sets, their connection to deep learning, vision, important applications. And something that kind of we've touched on a little bit all throughout the day is the role in thinking about low dimensionality in data of kind of mathematical model problems, what we learn from these problems by studying them very carefully, how that influences practice, and how the sort of practical insights that we get out of that then feed back into theory, creating even more interesting problems for us to study. So we've talked a lot about this very basic model of sparsity, of signals, sort of the classical theory. We can understand kind of at an engineering level almost everything that there is to know about how to efficiently reconstruct sparse vectors from very compressive measurements. And that's sort of been a model for us throughout these lectures towards understanding low dimensionality and deep learning as well. Of course, for deep learning, as Yaodong talked about, it's not enough to simply code data sparsely with respect to even a fixed dictionary, kind of in this linear model, but we want to also use data to sort of do some basic representation learning. In this very simple paradigm, the classical paradigm, we want to both learn a dictionary in which data is sparse, as we sparsify the data itself. So this gives another mathematical model problem, dictionary learning, which has a very rich kind of both theoretical and practical history. As Yaodong mentioned, it's also having a bit of a resurgence as sort of a tool for interpretability of large models in this day and age. But overall, as kind of a core computational paradigm in and of itself, as we've been talking about all throughout the day, both sort of basic sparse models, also dictionary learning models, through the sort of essential linearity assumptions that these models place on the data when we choose to compute with them, are not enough for really getting the most out of performance when it comes to data sets of the physical world, things that we're going to see when we start to try to apply sorts of these types of deep learning methods to real world applications in vision, robotics, what have you. Anytime we want to actually interact with these sorts of complex real world signals, we have to countenance and have ways to deal with essential nonlinearity in the data. And that's where deep learning has come in and sort of revolutionized everything in this field. We've been talking about that all throughout the day. But on this context kind of mathematical model problems, I want to think about this a bit and just sort of orient my lecture here, thinking about, so sparse reconstruction, dictionary learning, this has been really productive historically, both for having a very nice interaction between theory and practice and this sort of nice feedback loop. So when we're thinking about low dimensionality all throughout the day, understanding deep learning and vision as well, we want to think too about for deep learning. So what mathematical model problem kind of captures this interaction between low dimensional data, high dimensional data with low dimensional structure, and deep networks that we're using to process that. And so we've talked about compression, and this is a little bit of a reformulation of what Yi and Yaodong have talked about in their lectures. But let me just kind of crystallize that a bit into sort of a close to precisely stated model problem that we're going to call compressive autoencoding. So what we're trying to do in this compressive autoencoding, this is really just one way to formulate kind of a representation learning problem for high dimensional data. And so what we're after here is given a high dimensional signal X, We want to learn to map that to a structured representation Z. At the same time, we also want to do autoencoding here. So we want to have a generator as well that we can use to regenerate the original data from this structured representation Z. And the whole magic here is that we want to posit, we impose some desiderata that this representation Z should have. And that's what's really going to constrain this learning and make this resulting mathematical problem very rich and also useful for practice. So these are the same criteria slightly restated that we've talked about in Yi's lecture and that one of the questions at the end of Yaodong's lecture just touched on. So we want these representations to be compressed, right? Having only preserving sort of the essential, I'll use a vague word, low dimensionality in the input data X. So we want to get rid of every sort of bit of noise or even sort of nonlinear structure that's not essential to representing, processing this data and obtain compressed representations Z. We also want them to be linearized for downstream processing so that we can interpolate, extrapolate very easily in the representation space. And moreover, we want to have sort of sparse representations. So distinct modes of variability in the input data need to be mapped to kind of incoherent or even orthogonal components, say subspaces once we've linearized things in the representation space. We can impose as well that we might want explicit sparsity of the representations as well, rather than these being sort of arranged in any old arrangement of orthogonal or incoherent subspaces. Let's ask that they're axis aligned as well, so that things get easier to interpret. We don't have to do sort of large scale sparse autoencoding to interpret our large models. So how does representation learning look in practice today? I'll go through this quickly because Yaodong has already touched on this very well in his slides. But one of the most ubiquitous architectures these days, even in vision, we're starting to see sort of a convergence here, is the transformer architecture. And we'll review at a slightly more detailed level, although I'm sure this audience is very familiar with this architecture, sort of what are the building blocks of the transformer in a few more slides. But the main idea I want to get across here is just that there's this convergence, not just now in vision across different vision tasks, but also in computing with many different modalities of data, text, even sort of interactive decision types of state action data, towards using this common transformer architecture to process them. And as Yaodong talked about, kind of the perspective that we're advancing in this second session of this tutorial is that kind of the black box nature of these architectures, the transformer architecture, other deep networks as well, in spite of all the incredible practical successes that we've seen in terms of solving practical tasks with these architectures, leaves some things to be desired. There's some room to do better here. And so Yaodong talked a lot about understanding kind of scaling behavior, emergent phenomenon. Let me just mention here, in addition, that on the side of having a theory that can kind of shed light on these transformers, understand their inner workings, a lot of the existing theories, because of course, there's so much interest in different communities around transformer, that many folks have advanced different theories to explain what's going on here. But what you see when you dig into these theories is that a lot of them are actually kind of at odds with one another. Some folks are saying that the transformer is performing subspace clustering. Maybe there's a connection to certain kernel regression algorithms. Maybe the transformer is actually an interacting particle system. All these different, very interesting mathematical theories have been advanced to understand the transformer. But when you actually go and use a transformer to solve a problem, say doing next token prediction, doing detection, doing diffusion, which of these theories is really explaining what's going on in the transformer? Can I use these theories to actually make interventions when my transformer is not working? I need to do something better. It's not clear that any of these theories are really applicable there. So something else is sort of needed here. And cutting through this, actually having a theory that connects very closely kind of between both the practical aspects of using these models and also the mathematical and theoretical aspects, I think is really essential here. And we're going to try to advance such a thing, as we have been throughout the lectures in this second session in the rest of my talk. And of course, safety is a big concern here as well with black box models. If we have a better understanding kind of what the role of each layer in the overall model is, then we can do a better job of keeping the model transparent, making sure maybe that it's not used in malicious ways. So when we're using transformers, kind of just going back to the context of this compressive autoencoding model problem, when we're using transformer architectures, when we're interpreting these models with respect to this type of a model problem, compressive autoencoding. So it really, because transformers can do so well at very many different tasks where we have very high dimensional data, very structured data, text, vision, what have you, it sort of stands to reason that these models are very effectively learning representations for high dimensional data sets that we can use to do a lot of different downstream tasks, classification, detection, grouping, what have you. But because of the black box nature, the black box design of these transformer architectures, it's completely unclear, at least a priori from a kind of a post hoc perspective after we've trained the model, how to interpret or make interventions on those representations of the data that we've learned. The black box design is kind of standing in between us, having a guarantee with these very powerful models with respect to what we're seeking in terms of guarantees for the representation in this mathematical compressive autoencoding problem. So we talked in Yaodong's lecture about how to have kind of a basic, a basic prescription for an alternative here. An architecture, so we're calling these throughout this tutorial, this session, white box architectures, where you derive each layer in the network from unrolled optimization of an objective function that's kind of measuring quality of the learned representations. So we'll review that in this lecture as we sort of seek to kind of scale things up and make things a bit more performant. But Yaodong has exactly talked about how to obtain white box architectures kind of as an alternative to the black box design of standard large-scale deep learning approaches. The open question here, of course, because by the sort of virtue of their design, these types of white box architectures, like for example, the ReduNet that we talked about, is very explicitly seeking sort of compressed, linearized, modulo sparsity representations for high dimensional data. So that's good. The open questions here are maybe how can we actually, within this white box framework, how can we learn a corresponding decoder? We'll only talk very briefly about that here, although that's an important part of the compressed autoencoding, but we'll only have time to talk about the decoder very briefly, but also just the scaling performance. So how do we actually use these white box architectures on modern large-scale data sets so that we can actually get more insights into the data at that scale? That's what remains open after the previous lecture. And so I'm going to talk today about some basic modifications that we can make kind of at various resolutions of the pipeline that Yaodong described for designing an objective function, modeling the data, and then unrolling it in order to actually scale these white box architectures up, show that they can work, at a reasonable scale, and looking into kind of how they perform. So I'm going to start by talking about the modifications that are needed in terms of kind of the objective function. So again, we review a little bit. We have this sort of a framework for designing white box architectures that we've been advocating in the last two lectures, where the three steps are kind of first designing an objective function, which has as its optimal configuration, sort of optimal points, kind of representation Z. Again, this is an objective function defined on representations. So its optima should correspond to good representations that kind of satisfy the desirable properties that we've set out, say in this compressive autoencoding problem. So the first step is that design step. Then we unroll, we perform gradient descent on that objective function in order to obtain an architecture. And there are, of course, some choices there. Gradient descent is just one algorithm, and really we're just after optimizing this objective function. But there's another aspect of design here. How do we optimize? We'll talk about that in this lecture. And then finally, we sort of prescribe a scheme to actually learn any parameters of that unrolled network from data. So these are the three steps that we talked about in Yaodong's lecture. We showed how those look for Redu. And in this first part of the lecture, I'm going to review a bit, very briefly recapping and talking about the modifications we need to make for that first step, design of the objective function, to obtain something that's going to be more useful for a sort of large-scale visual data sets. So reviewing very briefly, these are just sort of a review of notation going back to kind of the quantities that are important for talking about this information gain objective function. So very briefly, we're going to go back to this supervised setting where we assume we kind of have high dimensional data X with corresponding labels Y. We use those labels to form this affinity matrix pi, which is kind of a one-hot diagonal matrix that's denoting which class each data sample belongs to. And then with those two bits of data, kind of the X's and the labels, we define this notion of information gain that, as we talked about in Yi's lecture, Yaodong's lecture, we can use to sort of identify and also transform low-dimensional distributions in the data. And so the way we do that, if we remember, is around this maximal coding rate reduction principle, which is based on the fact that this objective function, the information gain, in this labeled setting, as its optima, sort of representations Z that correspond to kind of configurations of sort of arrangements of the subspaces that are sort of partitioned according to these labels that we have in this problem, such that each class gets mapped onto an orthogonal subspace, and the dimensions of those subspaces are sort of maximized within the ambient space, using up as much space as possible. So that gives us a representation that's both compressed and linearized. We sort of get Gaussianity, linearity in the representations, and we preserve the essential structure of the data at the optimal points of this objective function. So that's kind of what we need within our framework. And our task here is to design a new objective function that still has that desirable property of its optima in terms of promoting good representations of the data. So we're going to talk briefly about 3 different modifications that we'll make in order to make this objective function more useful for general data. For larger scale visual data. So we're going to take kind of first a cue from the very ubiquitous transformers that we talked about in the introduction. So this should be familiar to the audience, but kind of the basic idea that we're using here is just that transformers, rather than maybe an architecture like the ReduNet, doesn't process data such as images in terms of simply as sort of a sample, but rather it splits those samples into constituent tokens and then processes them as kind of a sequence of tokens. So the operators in those networks are actually processing the data in a different way. So the transformer architecture has kind of this very simple structure where it begins with kind of a pre-processing layer and then iterates, several, we'll review the design, but just several sort of deep network layers, which we're going to call transformer blocks. And so the pre-processing layer basically just takes an input data sample, such as an image, and splits it up into tokens. For example, for images, these tokens are maybe in the most standard setting, non-overlapping patches in the image, arranges those kind of as, let's say in our notation, the columns of a matrix. As such, that's sort of a sequence now of tokens that we're going to process, and then performs just an affine embedding of that sequence of patches of tokens, let's say. So the pre-processing layer just tokenizes the data for images that's very simple to describe, and then applies a linear embedding. When we actually go to train these models, the parameters of that, affine embedding. So the parameters of that affine embedding have certain interesting structural roles in actually how the data gets processed by the architecture. But we won't talk about that too much in this lecture. So after the pre-processing stage, we stack these transformer blocks. And these transformer blocks are kind of famous as having this novel, in at least 6 years ago, and very interesting self-attention layer. So we sort of iterate these 2 operations. First is this multi-head self-attention block, which kind of computes correlations among all the tokens after performing some projections of them. And then based on those correlations, uses those in kind of a normalized way to recombine the data samples, so all samples, for each token in a certain way, sort of weighted according to those correlations. And so that's called kind of one head of self-attention. And in the transformer block, we use multi-head self-attention, where several of these heads are computed in parallel with different projections and then aggregated in a certain way to produce the output token representation. We have a skip connection as well, and we have some appropriate normalization applied. So that's kind of the multi-head self-attention block in the layer in the transformer. And then after that, we apply kind of a simple MLP, also with appropriate normalization, maybe just a 2-layer MLP with a skip connection for stability. And then we iterate these transformer layers in order to create the overall network. So the key operators in the transformer are this multi-head self-attention and the MLP. Kind of from a theoretical perspective, with regards to this context I mentioned about the theory explaining transformers, we want to understand a little bit about what the role of those different operators are. We'll come back to that after we make this modified objective function. But for now, we're just going to take this cue that it makes sense here based on maybe the practical success of the transformer. Instead of processing sort of, let's say, batches of image sample-wise, as we did in the ReduNet, and that is to say that the way we process them is by calculating this information gain, this rate reduction, on batches of samples of images. So instead of that, we're going to work with the information gain calculated on a sequence of tokens from one image. So that's what we're going to use as kind of the notion of compression that we're going to design an information gain objective around. So the modification here is easy to state. We're just going to sort of treat the data as sequences of tokens rather than samples. But kind of at a conceptual level, there's something very interesting there. Overall, though, as you see on the slide, this just gives us kind of the same objective function. It's just that Z has now a slightly different meaning. So that's the first modification that we're going to make. The second modification is going to be towards removing the need to have labels for data. One of the questions in the previous lectures asked about that. And so the way that we're going to do that is introduce some explicit modeling of the distribution of the data into the objective function. So previously, we were sort of using these labels in order to tell us a little bit about what are the different a priori modes of variability within the data, maybe assuming that the different classes have kind of different structures in them. Now we want to actually introduce some modeling of the distribution of the data so that we can sort of, through an eventual learning setup, learn what those different distinct modes of variability in the data are. And we're following a kind of a long list of works here that have kind of pioneered using signal modeling like this in this way in different white box architectures. But what we want to do is just kind of work this principle into an objective that's kind of like the delta R, the information gain. So towards doing that, what we're going to do is kind of introduce a parametric statistical model for the marginal distribution of each token in the representation Z. So this is going to look a little bit complicated on the slide, but it's actually easy to say in English what we're after here. We're just asking within this model. When I say asking, I mean we're kind of seeking. We're seeking to transform the distribution of the data towards a representation where each token, each column of this matrix Z, is marginally distributed as a mixture of Gaussians, low-rank Gaussians, where the covariance matrix of each Gaussian in the mixture is sort of parametrized by sort of these orthonormal bases UK. So we're going to assume that there's kind of K different components in this mixture that we're modeling the data as. Each of them is a low-rank Gaussian. And then the parameters of this statistical model become these different orthonormal bases for the subspaces. So that's the statistical model we posit. The trainable parameters now, or the learnable parameters, are going to be these subspaces that we're using to actually model the distribution of the data. And in a sense, you can think of this as kind of a generalization of the previous framework that we had, where we had this matrix pi that tells us how to segment the different samples of data up into different classes. That pi matrix is kind of analogous to these UK matrices here, in particular to sort of the outer product of these UKs, the covariance matrices of the Gaussians in the mixture. Then, given this statistical model, the way we're going to eventually obtain the information gain objective is by seeking to write down a notion of maximum information gain with respect to this model. So towards identifying low dimensional distributions in the high dimensional data X, what we're trying to do is find cases where we can do a good job of explaining our observations, like the current representations, in terms of this statistical model, measured through what's the coding rate, approximately speaking, of all the data versus the data's sort of representation with respect to this model. So the challenge here is that this model is sort of underdetermined. We've only tried to posit what the marginal distributions of each token in the model should be. So if we try to do what we did previously in Yi's lecture and kind of compute a good upper bound or a good approximation for the rate distortion of the data with respect to this model or of the representations, we'll find that that's an intractable problem. But we can always sort of compute a cheap upper bound, which is precise, which is quite tight in certain settings by simply taking the overall token representation Z, projecting those into each of the different subspaces, each UK in the statistical model, and then computing the coding rate for those projections, then adding those coding rates up overall. That's always going to be an upper bound for the true rate distortion with respect to this model, simply by virtue of the construction of the statistical model here. So what we get when we do that is something that looks kind of like the compression term that we had previously in the Redu formulation. So we have this sum of log determinants, but here sort of what we're plugging in are the projections of the token representation Z into each of these different subspaces. So that gives us, when we subtract that from this calculating sort of the overall coding rate for all the entire token set, a notion of information gain, analogous to what we had previously, in the setting where we had labels and where we were working with sort of batches of samples of images rather than sort of token representations within a single image. So finally, what we want to do here is make one more simple modification, which is sort of, it can be understood for interpretability purposes. But what we notice here is that in this objective function, this is also a property of the rate reduction that we defined previously in the labeled setting. There's this undesirable symmetry from the perspective maybe of interpretability of the features, where if we rotate all the subspaces in the signal model, and we also apply a corresponding rotation to the token representations Z, we get exactly the same value of this notion of information gain as we had before the rotations. So that's kind of a symmetry here. And this is something you can always get rid of post hoc after you can learn your representations by taking a PCA or something like that, that effectively quotients out the representations by this rotation symmetry. But for the purpose of incremental processing, which we're eventually going to want to do when we unroll this objective function into a network, and each layer has kind of different parameters, it makes sense maybe to get rid of this symmetry, explicitly sort of break it. So the way we're going to do that, and towards kind of having an objective function that satisfies all our desiderata, is to explicitly enforce that these representations Z are sparse. So that's going to be something that actually breaks this rotational symmetry, giving this objective function kind of a preferred configuration of the token representation Z. Rather than being aligned with any sort of orthonormal basis, they should be aligned with the coordinate axes. That helps interpretability as well. So with those three modifications, we're led to this modified objective function, very much analogous to what we had in the previous lecture, but with these important differences that make it more useful in practice as well. And we're going to call this kind of the sparse rate reduction, SRR. So that's the objective function shown at the top of the slide here. And so it hasn't been proved yet, but we expect, based on just sort of this intuitive derivation that we've described here, that just like we have this characterization of the optima of the information gain with labels in terms of compressed and linearized kind of representations of the data, these orthogonal subspaces with a preferred configuration Z. For the sparse rate reduction as well, we expect that the preferred configurations here are going to be sort of sparse versions of those same preferred configurations as previously. So in particular, this objective function is going to satisfy an MCR principle as well. And so by optimizing this objective function, we're going to obtain representations that actually satisfy our desiderata in this compressive autoencoding model problem that we talked about. So that's all for the objective function. Now I'm going to talk about the next step, which is how to unroll it. And going back to this sort of three-step framework that we've discussed, the way that we're going to kind of design an architecture from this objective function is via incremental optimization, sort of unrolled gradient descent. But kind of one thing I want to emphasize here in this derivation, and this sort of connects to some of the questions that we heard previously, is that one of the kind of perspectives that we're taking in this lecture, in this work more generally, is that we're going to give up on having, a little bit give up on having it be strictly enforced that each layer of this unrolled network corresponds to a gradient descent step, or in this case, a gradient ascent step. That's a desirable property because in many cases, you could have some type of convergence guarantee, something like this, inherited by the unrolled network from the underlying optimization scheme. That's not easy to prove, but in some cases, you might be able to have that. But we're going to give up on that here just so that we can actually do a better job of scaling these architectures up. Many cases, as we saw it for the RaDuNet, kind of the gradient operators that we get when we do unrolled gradient descent on those objective functions are not very scalable to compute. So we're going to look for efficient ways to approximate them such that when we kind of empirically evaluate the operators that are learned by the network, and I'll show experiments to this effect later on, we see that the network actually is kind of on an empirical level performing an approximate optimization of the underlying objective function. That's something we can calculate just because we designed the architecture to optimize this objective function. So I'm using these words here on the side, approximate gradient descent. And that's what I'm sort of, the terminologically speaking, I'm using to denote the kind of what I'm saying out loud here. And that's kind of a shift of paradigm versus a lot of the work that's done on unrolled optimization. And it's all motivated by kind of scaling these things up. Okay, so we're trying to unroll this sparse rate reduction objective function, kind of an expectation of it in the generalization sense over the data distribution X. So we're trying to optimize this objective function. And as I mentioned previously, the design choice now for unrolling is just how do we actually perform this optimization? So what we're going to do in this work is just talk about a very basic scheme to optimize this objective function. We're going to split it into two different terms and perform kind of an alternating approximate gradient ascent on these two terms. So I'll take a gradient descent step on one of them with approximations made for efficiency, and then we'll take a gradient descent step on the other, and then we'll iterate those two steps. We're kind of grouping these based on the intuitive, the derivation of these two terms as kind of a compression term, one that kind of promotes compression of the representation, and a sparsification term, one that promotes that the representations are sparse. And now that we've done this division, we've decided that we're going to do alternating optimization. Now the design choice that's kind of left to us is how do we actually optimize each of these two terms? So first, I'll talk about how we optimize the compression term. So we're kind of, I'll just give the sort of high level takeaways from this derivation, although there's kind of a few calculations denoted on the slide, and we can talk offline if you want to know more about the derivation. But what we're going to do here, after we flip the sign on the objective, is just take an approximate gradient descent step on this compression term towards compressing the features. What we see by making a few judicious approximations in the gradients of this compression term, and I think this might have been alluded to in some of the previous slides, but what we see is that after making appropriate approximations and adding some notion of normalization here for stability, a gradient ascent step on this compression term actually has a functional form that resembles very closely the multi-head self-attention layer with skip connection in the transformer architecture. But there's one key difference here. So the key difference is that the different projection matrices in the transformer's self-attention layer, these query key value QKV projections, in this kind of derivation of the architecture from this compression objective, the sparse rate reduction, these QKV matrices are all the same. And actually they correspond to these different subspaces that we posited as like this local signal model for the data. So there's this kind of connection that's being made here at a formal level, at an approximate level as well, between performing compression of the local token representations against our signal model for the data, this mixture of subspaces parameterized by UK, and a multi-headed self-attention operation where the different heads correspond to different subspaces, and the projection matrices in each self-attention, QKV, are all the same and corresponding to the bases of these subspaces. So this is an interesting interpretation that we kind of get out of this derivation of the type of operation that a multi-head self-attention layer is transforming, that is performing. So that's for optimizing the compression term. We get an operation that's quite analogous to multi-head self-attention. And as for kind of optimizing the sparsification term, what we're going to do, this derivation is a bit long-winded, but basically what we're doing is choosing one simple way within kind of the overall space of directions, kind of local directions to improve the value of this sparsification term. We're going to pick out a much simpler subspace to compute with, and then kind of incrementally optimize along that direction. So that direction is going to end up corresponding to kind of an auxiliary parameter that we introduce here, which is an orthogonal dictionary D. So we introduce that parameter and then seek to just sparsify the features that we get after compression with respect to that dictionary. So rather than optimizing this sparsification term among all directions, just among those directions that correspond to sparsification with respect to this dictionary. The reason for introducing this dictionary is that it simplifies things a bit. So in particular, because the dictionary is orthogonal, kind of optimizing along these directions doesn't change the value of this expansion term R of Z at all. So that doesn't play a role at all when we're moving along these directions. And then the problem of incrementally optimizing this term just becomes equivalent to this sort of sparse coding problem that's shown at the bottom of the slide here. So we're doing sparse coding, in effect, with respect to this dictionary D that we've introduced. And then we can play the usual games that we talked about in Yaodong's lecture. We can relax this conceptual sparse coding problem into kind of a Lagrangian form, relaxing the L0 norm into its convex envelope, the L1 norm. And what we end up with then is that this local optimization problem ends up corresponding to kind of a matrix lasso problem. And so we know, just based on what we've been talking about all throughout the day, when it stops, I think I'll be back. Maybe it won't stop though. Okay. So what we've been talking about all throughout the day is how to actually solve that matrix lasso problem, recalling this proximal gradient descent algorithm. So if we iterate that algorithm infinitely, we'll converge exactly to the optimizer of this matrix lasso problem. We'll choose here in the spirit of local approximate gradient descent, just to take a single prox gradient descent step on this problem. So what that ends up doing, as we've talked about throughout the day, is applying this certain affine transformation of the output of the compression layer, that layer that corresponds to the kind of the multi-head self-attention operation in this overall architecture. And then applying this sort of, here it's a ReLU function, but something sort of like this soft thresholding function is being applied after that. That's what we get by taking a single gradient descent step on this matrix lasso cost. And so what's interesting here is that you can interpret this layer as being quite analogous to the MLP block in the transformer architecture as we discussed previously. So applying an affine operation to the representations and applying a nonlinear element-wise activation to the result. So the linear transformation here is parameterized by the sparsifying dictionary D from the derivation. And maybe the key difference here with respect to the transformers MLP is that this operation sort of explicitly sparsifies the representations by having, in sort of an informal sense, the skip connection in the architecture inside the nonlinearity rather than outside it. So that's one difference from the standard vision transformer architecture here. And that actually leads the representations that we're learning here to become explicitly more sparse, unlike in the typical vision transformer. So once we have those two operations, we've now performed one incremental step of optimization, approximate optimization of this sparse rate reduction objective function. And now we can iterate those steps corresponding to kind of layers in the unrolled architecture. And that actually gives us the overall architecture for optimizing this objective function and transforming our data towards more compact structured representations. So we compose those, some number of times. And so we call this architecture crate. And kind of just to summarize this derivation, the two main differences between crate, this transformer-like architecture, and the typical vision transformer architecture is that in this architecture, so we have operations that are quite similar to the typical transformer layers, but the projection matrices in the multi-head self-attention layer are all the same in this crate architecture derived by unrolling the sparse rate reduction. And in the MLP block, we use this ISTA operation instead of a typical generic MLP with a skip that explicitly sparsifies the features. At a high level, these are the two main differences between this architecture we've derived and the typical vision transform. And so now that we have this derivation, we just need to sort of think of a way, and here we can sort of use any typical prescription, since the architecture is quite analogous to a vision transformer, any typical prescription for training transformers that we can add from the literature. So we're going to learn the parameters of this model from data. So we have kind of these two optimization operations, as Yao Dong talked about in his talk here, that are going on. Like forward propagation through this unrolled network is optimizing this underlying objective function that we derive the layers of the network from. So that's kind of this forward optimization process that's in an interpretable way, transforming the distribution of the input data towards a more compact and structured representation. But then also when we learn the parameters of this network that is actually doing this forward optimization, we're doing backprop or something like this, right? So this is a different optimization operation for learning these parameters. We'll call that kind of the learning process, the backward learning, analogous in that very simple ISTA example to kind of sparsifying the data, learning the sparse code, and then learning the dictionary, actually within which we want to sparsify the data. So we have the same sort of thing going on here in this crate architecture. So in the experiments that I'm going to talk about today, I think we'll mostly be sort of doing classification-based training for this crate architecture. So the way we're going to train it here is just with standard kind of append a class token or prepend a class token and then train the network in that way. It looks like we are.
Yeah, sorry, I'm trying to.
We're a bit more balanced now. Thank you, guys. Okay, so now to wrap up the lecture, I'm going to talk about a kind of a suite of different experimental results that hopefully show that the architecture we've derived is pretty promising for different applications with visual data. So we're mostly going to be applying this thing here in analogy to a vision transformer, so working with images and things like this. So first I'm going to show some simple experiments, just trying to verify that the approximations that we made in this approximate gradient descent that we used to derive this crate architecture were well justified, so that we actually obtained an architecture despite approximations that indeed optimizes the sparse rate reduction. So the plots I'm showing on the slide here are just a simple experiment. So after kind of setting up the parameters of this crate architecture in a certain way, analogous maybe to how one would configure the parameters for a VIT, and then training it maybe on Vision ImageNet 1K. I'm looking at sort of a batch of val data as I propagate the sort of token representations of that batch through the neural network forward. On the x-axis here, I'm sort of indexing by the layer of the crate network. And on the y-axis, I'm calculating these two different terms that we sought to optimize from the sparse rate reduction. So in the left plot, this is the value of the compression term that we actually tried to do approximate gradient descent on when we derived the compression block corresponding to this multi-subspace self-attention operation. And on the right, I'm just calculating the sparsity, the number of non-zero entries suitably normalized at each of the representations at each layer after applying this ISTA block analogous to the MLP. So what we see is that through forward propagation on these batches, averaged also in a pretty reasonable sense, so the error bars here aren't too bad. We are kind of in kind of a suitable amortized sense, optimizing the sparse rate reduction objective function as we propagate forward throughout the network. So despite the approximations that we made in the derivation, this architecture is performing its design function here. And just as a basic sanity check, we see that kind of at random initialization of this network, the architecture doesn't do a very good job of optimizing the objective function. This is maybe something that only a theorist would think of as a sanity check, but here it might be thought that some sort of implicit bias is actually corresponding here to the fact that this architecture that we get after training is optimizing this objective function. And this experiment is ruling out that possibility. So it's sort of a resounding no. Actually, it's completely due to the learning process here. After learning, only then do we obtain kind of parameters of the network, the projection matrices and the sparsifying dictionaries in the ISTA block that do a good job of optimizing the sparse rate reduction. So there's something interesting going on here. And in the derivation, I'll just spend a very brief amount of time on this, but in the derivation, most of the parameters that we introduced, the sort of subspaces for the signal model corresponding to the projections in the multi-subspace self-attention layers, and also the sparsifying dictionaries, we posited that those were orthogonal. So what we see when we actually calculate is that even if we don't explicitly enforce orthogonality, which would be kind of inefficient in the training, we end up with subspaces that do a very good job of covering the space. So we learn subspaces that are quite incoherent in this sort of aggregate sense. And we see these sorts of very concrete sort of sparsification and low rank properties emerging. This is sort of forward propagation, kind of in raster order here, of the token representations from a single image after training propagated up the network. So these representations are indeed getting sparser and more correlated as well. Next, I want to show kind of an interesting observation that we had here, which is that, so this crate architecture, even when it's just been trained sort of in this typical classification on ImageNet 1K, sort of class token kind of cross entropy training of the representations. So even with this simple training setup, sort of the self-attention maps in the penultimate layer of the network actually do a pretty good job of segmenting objects in input images into different parts. So different heads here are actually corresponding to segmenting different parts. And this is something that at least in prior work, sort of prior maybe to like iClear of this year, you could only observe with vision transformers after applying a very delicate blend of lots of different training tricks, self-supervised learning tricks, sort of very intricately set up in order to make it be the case that in the trained transformer, the trained vision transformer, you would have this sort of segmentation behavior of the input tokens through these self-attention maps in the network. What we see is that, maybe as a consequence of this interpretable design of the architecture, we actually get this emergence of segmentation essentially for free, just from training on the typical class token supervised cross-entropy training. And if we look a bit further into this phenomenon, we can see in kind of an interesting way that there's also this semantic property of the segmentation that's being performed by different heads in this model. So what I mean by that is, for example, across different object classes here, sort of in a consistent way, different heads in these multi-subspace self-attention blocks are segmenting different parts of these objects that have a common semantic function. So different legs across different animals, the head part, what have you. That's kind of what we're highlighting on this side. And it's interesting that this is maybe an emergent property in this model simply by virtue of the alternate design. So there's something very interesting to be understood there at a deeper theoretical level as well. And we can talk about kind of basic performance metrics for this architecture as well, just to show that in spite of this interpretable and more constrained design versus the vision transformer, these architectures can be used to learn useful representations of high-dimensional data sets. I'll show some more recent progress at the very end on scaling up, but these are some basic results just on sort of supervised classification training on ImageNet 21K and then fine-tuning evaluation on ImageNet 1K or different data sets. What we see here is that kind of a base configuration of this crate model, sort of named in analogy to the different configurations of the vision transformer, is achieving pretty competitive classification performance here with respect to vision transformer of a comparable size. So if we just count parameters directly in these models, the crate models are going to have less parameters in the corresponding vision transformer architecture because of the fact that the query key value projections are all the same in crate. And also the ISTA block is slightly more constrained in terms of its ability to be over-parameterized as well. So there's a bit of savings there as well. So if we compare, kind of try to do an apple-to-apples comparison in terms of parameter counts, what we see is that these crate architectures in this supervised classification task are showing some promising ability to scale up. I'll show even more recent results for improving this performance further. But at least as a sanity check, and compared to the types of architectures that we saw in the previous lecture, this is quite a step forward in showing some promising performance. So finally, something that's a little bit interesting here. So two final kind of experimental observations, building a little bit off of this semantic segmentation of the different heads behavior that we saw kind of at a qualitative level in the previous slides. We can also show that the alternate design of this crate multi-subspace self-attention layer, again, where the query key value projections are made all the same, can be a useful design for doing segmentation in other tasks as well. So in this experiment, what we're doing is sort of simply taking in kind of a typical zero-shot clip semantic segmentation pipeline, just swapping out and sort of projecting in a certain way in order to do the swap. Swapping out kind of the architecture of the self-attention block in the penultimate layer of the vision model that's being used to do that segmentation in the VIT, the clip VIT, for the crate block. So we're just doing a straight swap. There's no parameter tuning that's being done here. And after we make that swap, we actually see very good performance in terms of the zero-shot semantic segmentation behavior after some post-processing being applied as well for some of these segmentation maps. So this is actually showing that in terms of quantitative metrics as well for this type of a grouping task, this crate architecture, and specifically this multi-subspace self-attention that we get from unrolling compression, is quite useful here. And so one last verification, very, very basic, but we can also show that with suitable modifications for enforcing sort of a causal structure, this type of a crate architecture can be used in text tasks as well for sort of doing some autoregressive prediction, or sorry, a next token prediction in kind of a GP2 style setup. So these metrics don't read too much into them at all, other than maybe they show the fact that this architecture can be trained, so it can learn some useful things. There's a lot more work to be done here to really get it to scale up to large-scale text data sets. But there's at least some promising ability to learn in this alternate modality as well. Okay, so let me now very briefly, I've talked about crate. I've shown hopefully that it's promising in some different experimental settings with visual data. I want to describe briefly some interesting emerging directions as well around these types of white box transformer-like architectures. And then I'll wrap up the tutorial with some closing remarks. So the first thing, I don't have a time to talk about this in great detail, but we talked at the start of the lecture about this model problem, compressive autoencoding. So we want not just to be able to learn structured representations for high-dimensional data, but also have a way, in kind of an analogous white box way, to map those representations back to data so that we can maybe do training without having labels, sort of doing a full end-to-end unsupervised training, other tasks as well. So what we show in some recent work is that, so in order to kind of derive a corresponding white box architecture for this decoder, corresponding to this crate encoder, one can exploit kind of an interesting connection between this compression operation that is sort of the backbone of crate and kind of a denoising operation, this very ubiquitous statistical operation, which is appearing everywhere. And in particular, these days, denoising is kind of a key component of the diffusion model for actually generating photorealistic samples from natural image data sets. What we use in this setting is based on this correspondence kind of between compression and denoising at a certain resolution. And the correspondence, this sort of distribution-wise invertibility between architectures that denoise iteratively and architectures that kind of diffuse in the other direction. So we sort of show how to invert in kind of a white box way a crate architecture that's doing this iterative compression across layers. So by this connection between compression, denoising, diffusion. So this is giving an architecture now. More needs to be done to evaluate it, and there's lots of exciting ongoing work here. But they can actually be used in unsupervised pipelines, learning representations in a much less constrained setting. So there's also some recent work that's been done on scaling up these crate architectures as well. So by a suitable modification, among other things, the key modification here is maybe a way to make the crate ISTA block, which is analogous to the transformer's MLP, more scalable. So it can actually be, we can actually do a much better job of scaling up these crate models. So improving performance in a way that's kind of commensurate with how the typical vision transformer scales as we increase the model size and the data set size. So this is maybe a much more promising way to scale this model in terms of the practical performance compared to the results I highlighted previously, which are very basic. And so as I alluded to, we can talk more about this offline if you're interested. But the basic modification here is to make an MLP block kind of analogous to the ISTA block in crate. It's more analogous to an overcomplete dictionary learning rather than the orthogonal dictionary learning that we kind of posited when we derived the crate MLP block. So this is giving you an MLP analogous to the usual vision transformer. They can be over-parameterized a little bit better and maybe stacked for multiple layers in some sense, and ends up being much more scalable, helping to improve performance while still retaining this important connection to kind of sparse coding that is the backbone of the crate ISTA layer. And finally, there are kind of a lot of different axes as well that can be explored for how to design different kind of compression objective functions and optimize them. So there's ongoing sort of a recent work that's been done as well to kind of design an alternative layer to the typical, to the crate MSSA layer that achieves kind of linear scaling, linear complexity with respect to the sequence thing. So this is kind of derived by using different signal modeling assumptions on the data. And so this is another example of how kind of once you know these basic principles of writing down the objective function, unrolling it, you can start to see how different modeling assumptions and different unrolling techniques actually give rise to different architectures with useful computational properties in practice. Okay, so let me wrap up the tutorial briefly. So we've been emphasizing all throughout the lectures today, kind of this perspective on deep networks as being sort of inextricably linked to how they're identifying and transforming low-dimensional distributions in high-dimensional data sets towards more compact and structured representations. So especially in the second session today, we've seen how these types of operations, which are sort of essential to the representation learning problem as we know it in general, are really inextricably tied to kind of this notion of low dimensionality in data and how deep networks sort of seek out low dimensional, compressed, compact representations for low dimensional distributions in high dimensional data. So in the first session, we talked about how kind of in general deep network architectures, when you have, in some sense, kind of an unbounded or unlimited ability to either have lots of data or optimize different objective functions, you actually see that there's sort of this inevitability of low-dimensional structures in deep networks trained on very general high-dimensional data sets. So in some sense, even if you set up these very black box learning problems with typical architectures, just by virtue of kind of the construction of these different learning problems, you will sort of see low-dimensional structures emerge, whether in the operators of the networks that you learn, whether in the feature representations of the network throughout the layers of the network. They correspond to these classical notions kind of from low-dimensional sparse and low-rank representations. Operators in these networks that perform compression-like operations and signal sort of representations for the data that become sparse. And we saw in these in this first session kind of how to use those insights to do a better job of performing, in some cases, parameter-efficient training, transfer learning, and things like this. And we've talked in the second session about how kind of in a complementary perspective, going from the bottom up, how once you've clarified that this is the representation of learning, now you can use that sort of perspective to design deep network architectures that are sort of by virtue of their construction, performing this task of identifying and transforming low-dimensional distributions in high-dimensional data towards more structured representations. So we talked about this design framework, kind of writing down objective functions that quantify different notions of information gain for the data, using those to identify low-dimensional distributions, and then unrolling those objective functions to actually go from measurement of these low-dimensional structures in an indirect sense to architectures that kind of seek out how to transform the data towards those structured representations. Once we do that, we've seen that these derivations, so just the fact that we have derivations, give us sort of more interpretable network architectures. We understand at a mathematical level what the role of each layer is in transforming the distribution of data towards the representation. And it also helps us to eliminate certain superfluous pieces in the overall architecture, kind of clarifying these different roles of the different operations in each layer, shows us what's essential, lets us take away what's not. So I hope this tutorial has shown you kind of the utility of thinking about these notions of low-dimensional structure and data, learning a bit of theory, and how that can actually help with designing, pruning, parsing, kind of different issues that one runs into when you're computing with visual data and deep networks. So with that, I'll wrap up the tutorial. Thank you for your attention. And here's a few links to some of the work that I talked about in these last sessions.
I'm trying to wrap my head around the fact that the QKD matrices are being equal.
Yes.
So do you have so what your intuition have? So I tried, I don't understand why they be equal. The question should be around why they should be different. Different is easy to imagine, right? So you have to it's because you have the names that have to be different. No, so this is a very simple question. Is that so why they're the same? Because they're the same codebook. You're actually projecting the data. That's just a set of codebook that we each had. That's the codebook to capture the low-dimensional structure along that direction. So the data gets projected. Each subspace actually think about as a view of the data. The joint distribution gets projected onto different slices. It's actually mentioned related to one of the sliced mutual information. I have to look into that.
Yes.
Okay, that's one to making the mutual information computable. But here is it's basically I have a joint distribution, very complicated. I don't know what it is, but I can possibly projecting the joint distribution to different low-dimensional subspaces. I code it there. So that self-rotation is just a covariance of that. In the part of the Weiser operator, minimizing the covariance. There is no need of KB unless you maybe you do in a separate variable that you do the conditional estimation, conditional sampling compression. So you compress X, get a Y, then you have a cross, attention cross. Forms. But if you just compress in the data itself, there should be just one correlation.
Yeah, that makes sense. Thank you.
Thanks for the talk. That was lovely. In the previous lectures in the tutorial, the sparsity was kind of motivated by the problem itself, like the classification of the clustering problem.
Yeah.
And in this case, you motivated it by saying that you have this ambiguity is the rotational invariance or rotational symmetry, and you use the sparsity as a way to
Really,
choice of basis.
Yes.
And then at the end, it turned out that the sparse coding was one of the bottlenecks in the computation. Is it necessary to include the sparsity regularization, or could we do a different approach to fixing the basis, like Riemannian optimization or something like that?
so absolutely. So now you know what you're doing, right? So all the things you saw today are sort of the naive, basic way to try to make the representation towards what we the measure we want. So once you realize that, I mean, what we're currently doing is not necessary, right? There are other ways you can actually, can be replaced potentially by other operations have the same effect. So all you know that there's just one of the features spec, and also kind of sparse aligned with axes. In fact, even the work that he mentioned briefly about the token, they go back to the no, forward this yeah, this one. Yes, I'm sorry, no, TSSA.
TSSA.
Yeah,
I only have
so
the
this
block.
one. So this is actually also realizing that precisely also realizing that we don't mention, we don't have to do the compression the way it is. And there's much more efficient way you can replace the rate, consider a variation form of it. And then that can be computed, even the denoising part, compression part can be computed much more efficiently. So you can think about the current rate is actually probably the most naive from an optimization point of view, of the most naive straightforward. Just to descend of these two terms. But you can also potentially do them simultaneously. You can even those operators, you can use that if you know really what effect you expect them to. Right. So this is actually what makes this a little bit more exciting is now you know what your the object function is. And then all the ideas, great ideas from optimization go into helping to design better, much more efficient operators to achieve the incremental optimization, more efficient per layer. Also more efficient than operation itself, it's more compute. So to me, I really think we're just scratching the surface. Right? There's how many versions of optimization? You know how many different versions of the gradient descent? The first order method. We haven't even close all this, even first order method, acceleration. Nobody had even considered that.
Yeah.
Right. So in terms of design architecture, we're at the beginning. Right. Once we realize the architecture has come from optimization, we haven't really used any preliminary ideas from optimization to help us design much more efficient operations. Right. You see, from this perspective, right, if transformer is to emulating this kind of optimization, even though this current crate is the most likely basic construct the reading set.
All right, if there are more questions, let's take them offline, but for now, let's get ready for the panel session.
Yeah, I think we're like five slides.
You just feel free to
There's two here.
read.
Oh, okay, then.
Two chairs here.
Yeah, more
Do you
chairs.
want to have from, who is moderator?
I'll moderate.
So you can sit there or?
I'll stand
If
here.
you want
sit
to
over
stand,
there.
or you can just stand. I think you just stand.
Sam, you can also. Or-
Also, I think that. Okay, yeah, the same. Turn it off. Or maybe because of one thing that and do you want to use this one or not?
Oh, we can use.
Kind of one second maybe, because this will be.
Oh,
It's dropped, yeah.
maybe can we move a little bit?
Yeah.
Um,
I will take the book.
Maybe you can move the chair a little
Or
bit.
maybe you can put a little bit of the back here.
Yeah, sorry.
I think you can move over here.
Yeah, further.
Okay, I think it now.
I'll stay here separate.
Okay.
You want me to be on that?
Yeah, maybe it's up to you. Up to you.
Maybe I'll sit up.
Okay. Does it work? Oh.
Yeah, it's.
Extra charger.
Yeah.
Let's do.
Can just keep that here.
Okay. Okay, the last session is a panel discussion. I'm the moderator, and we have Professor Ima from UC Berkeley and HKU, Beili Chen, Professor Beili Chen from CMU, Wu Yang from Simon Fraser University, and Mojin from Microsoft Research. Sam is there. So before I start, I mean, the panel will have 4 questions. And afterwards, it's free debate between the panelists and the audience. Yeah, so before that, I want to use this opportunity to advertise a little bit. We have a new conference called this Conference of Parsimony and Learning. So the first conference takes place is at HKU. Thanks for Professor Ma for hosting this. Actually, this is we just started this from a workshop to a conference because there's so many large conferences and so many papers. So we want to have a small conference focus on sparsity and low dimensionality for understanding and advancing machine intelligence. And actually, the second conference will be confirmed will be at Stanford next spring. We are still fixing the time, and the submission deadline will be around early August. So every accepted paper will be presented as oral. And it's roughly, we expect roughly like 50 papers to be accepted. So actually we have our new, I used to be the program chair of the first conference, and actually we have the new program chair, Professor Beidi Chen here. And also Professor Ma, the general chair. Whether you want to add more comments on this?
So I think now there are so many mega conferences, right? The review system, I think, is broken. And the quality, I don't think, everybody says that already saw the top conferences, still top conferences, they're all entering level conferences. So this is the idea trying to bring things back a little bit. But I think a lot of the bigger conferences have lost their function as truly a platform for academic exchange. So we want to put some constraints to the conferences. Basically the conference has to be hosted on campus. Basic facility of, so that limited the scale to about probably 200 people, 200 or 300 people. The auditorium can host comfortably, and also that the restricted scale, and also the focus will be, the conference will be more focused, right? So here's a question, what paper Europe's does not publish? It's published every subject. So that's actually very, very diverse. I think we want to be more focused, and the also to have better quality control. And the smaller side, people have enough. And also all the paper accepted will be oral. Make sure that there's a very fixed number of papers to be accepted and have a chance to present your work. And so that's basically the idea. Also, that the conference will consist of probably half of the talks will be invited. And we'll invite people that with the work that we think has published and in the past couple of years really has good quality and impact. So that's basically the conference is trying to maintain bring back some of the standards, quality control. So since it's also small, we can only accept a few, much less papers, and then the review process will be, the quality will be much higher. But that's actually fair.
Yeah. Also, I want to add is that we will evaluate the TMR where the area chair, I mean, for the AC, when they make the decision, the name of the AC will be revealed. Yeah, so that's like the associate editor for TMR, right? They will be, the AE's name will be there. Yeah, so next let's start with the questions for the panelists. So the first question is that what are the central questions that remain unanswered for us to understand deep learning, and how can this be achieved by exploring the low dimensionality in terms of data and models? Maybe we can start from Sam.
Have a mic. Is that one coming? Okay. No.
Okay.
So I'll try to just give one answer that which will probably be different from maybe a theoretical perspective. What is left to understand about deep learning? And in some sense, I think you can take very extreme perspectives and support both of them. So in some sense, we don't understand anything about deep learning theoretically. You might say that, I mean, we talk in this conference or in this tutorial about, sort of a fairly complete theory of deep learning in some sense. It allows you to do something about being able to design architectures that have certain properties. It can also scale up well. But if you talk about a very rigid sense of what it means to understand things theoretically in terms of maybe like in the sparse representation sense, we can prove theorems that say exactly when deep learning as an algorithmic procedure works and when it doesn't, when it fails, why, what types of data sets it works on, what types it doesn't. In that sense, very little is known. And most of the theoretical effort is going towards studying very shallow derivatives, trying to make some basic prescriptions on what happens there. So I would say from that type of a very rigid theoretical perspective, we need to really understand deep learning, not just 2 layers, but maybe 3, or preferably 10, 12 more. And there's a lot to be done still, I think, at a very theoretical.
So, so I can, I think there are 2 things troubles me, right? So, one is that, we don't know right now so far, we don't know rigorously mathematically that what is the property of the distribution of the data. We should make assumptions on. Yes, for limited case, we can say mixture of Gaussian, mixture of subspace, mixture of Gaussian, or mixture of manifold, right? But there's a lot of correlations. All the analysis so far based on maybe assume they maybe come from mixture of Gaussian tokens, but that's just marginal distributions. What about the joint distribution? What type of property they have mathematically? We can put our fingers on, can quantify. We can, at least qualitatively or quantitatively, what property about the data and are available for this kind of and we can actually extract. We can actually code them compactly, right? And help us to do prediction. So the representation we learn and do classification or generation effectively. That's still unclear, right? So this is one. Another thing is that about the network performance. Right? So yes, we sometimes say we can actually probably understand maybe neural networks right now in this framework. Maybe they try to achieve to do kind of contrast, to do compression, denoising, or specification. Right? But the efficiency is nowhere near they should be. Right? Our brain is probably dozens of layers, probably less. And here we can say right now it's still, quantity is 30, whatever, 50 layers and so on, right? And also the neural networks right now, we construct them the operator of this agent, the denoising operator is not grading descent. But is grading descent the most effective way to compression? No. Right? So, and if you really want to, what is the ultimate efficient way to get converge on those low dimension structures? But that's the most effective family of operators. We don't know, right? And my guess is that those operators will rely on very scalable, information you can compute very scalably from the data, very high dimensional and very first order information, but they can be used to construct much more effective operators that denoise or compress, so that you can converge on the structure by efficiency. We don't know what they are yet. So far, as I said earlier, the grading descent is sort of diversified. But in terms of efficiency, we don't know if there is the best and most efficient one yet. Two things. Assumption about distribution, is that what the most effective way. Given this distribution, what is the most effective way to learn this distributions?
I think I completely agree with Professor Ma, and I just wanted to add one little thing is that I feel like for like question 1 specifically, something that has been happening for as long as deep learning has been around, is that the biggest impacts or like things that kind of like push to the next step are always very heuristic, or like something that is just like someone put something together with trial and error and then created something that was like much better or scaled up something. And the theory is usually followed. Like when something works really well, then people try to kind of like really study and gain intuition on why did this happen. But I think I completely agree that just because those things are with trial and error, then what happens is that they're not necessarily like the most optimal or the most efficient way to achieve things, or even we are not achieving the best performance that we can. So my hope is that like all of these theory and studies, especially like on low dimensional computations, everything that discussed like in the tutorial today, if it can kind of catch up and predict the next step based on theory, then we would be in a much better position in the future. So I think that's the hope.
I do appreciate all the pre-discussions, and from the theory perspective, I think I can point out perhaps one of the most important bottleneck. I think many theory people will agree that the training dynamics, the gradient descent dynamics, is one of the most important bottleneck we want to solve. So if we take a look at the current theory tools that we developed so far, I think we pretty much have a very good understanding of the levels at each transition. Either the Gaussian process or your attention kernels or in the regions, we have good characterizations of the properties of the network at each transition. But as long as we try to move a little bit far from the transition, either small learning rates like free and flow, or large learning rates where people believe that that makes example learning features, we probably fail to use any tools to categorize this process. We can also try to categorize pre-trained models with some random matrix series. But from the beginning to the end, this whole process, we really cannot find two ways to categorize. So I think if I would like to pick one key bottleneck in front of us, I might choose the training dynamics. And the low-dimensional models can definitely be helpful because right now most papers, for example, try to freeze part of layers and allow us to only update part of layers so that it can be easier to analyze. That would be my answer.
Yeah, I want to complement the previous great discussion on this question from the practice or algorithm hardware co-design perspective. So I work on MLSys from the perspective of like sparsity or low rank matrices and structured matrices, all these structures. How can we leverage all these structures to do things more efficiently on given hardware? Could be CPU, GPU, and all the other ones. And talked to Yang last week on he really likes NVIDIA, obviously, just because all these algorithms, like or deep learning with the hardware, they're just powering each other, right? But the problem that I kind of see now is there's one kind of type of power kind of constraining all the computation to dense matrix multiplication. And then that kind of biases how our efficient architecture design. I work on algorithms like the quality simplification and all these matrices. And like because of the hardware perspective, random sparsity doesn't run actually faster. Even theoretically, it's bigger one, it does not run faster. And then the other examples on a lot of calculation run fast on CPU, algorithm like n log n, but it's slower than what you can parallelize everything with n squared. So I'm just giving examples on that kind of like limits our architecture or the efficient architecture designs. So what I want to kind of understand is what are the primitives for the deep learning to work? Can we abstract it in a way that we could still using like a collaborative CPU, GPU, and whatever hardware to kind of not constraining on the most advanced and waiting for NVIDIA to produce all these H100s or GH200 and all the kind of more advanced hardware to run things faster or more efficient. So I'm just like commenting this on a very practical and hardware kind of co-design perspective, such that like everyone can work on a more efficient algorithms, or they can just work on in their desktop, like there's a concept of like AI PC and all the rest, so that everybody can be creative and designing the algorithm that they think that makes sense, and then not everything should be like a matrix multiplication or dense matrix multiplication, and especially like it's not very friendly to like sparsity and some of the things that are very efficient theoretically, but in practice, it's just taking longer time to run. And then I guess like that kind of complements a little bit on the like theoretical perspective on what I want to understand of the deep learning is like what are the most necessary components of to make the deep learning or all these models to work, and then can we make them run faster on a limited resources so that people can be more creative on getting the next generation of the architecture design and the rest.
I just just want to add, since you guys talk a lot about the algorithms and optimization, right? I think, this is the biggest challenge of the network is if you guys really want to deploy efficiency, really change the optimization strategy. But right now, if we still live in the back propagation world, there's no hope. And nature does not do back propagation. All right. So, so one of the things we saw in this forward construction is that in fact we can do forward construction. Forward can optimize. You don't have to rely on learn everything from scratch. Nature does not build a deep network and optimize end to end. And so if you do that, you are still in the megawatts. Which you can never cut probably a couple factors. So hence, how do we combine forward and backward? And we cannot do the global optimization, right? The biggest challenge is one of the optimization strategy allow us to do local, parallel, right? Layer-wise, loop-wise, rather than, they still can achieve global efficiency, converge. It might take a bit longer to converge, but eventually end up is converging to much more faster efficient optimization, right? Achieve this forward, backwards optimizations, encoding, decoding schemes, right? So that's actually the biggest challenge. If you think about optimizing, think about the algorithm efficiency, right? We can never really achieve efficiency by still doing global, optimizing all the parameters simultaneously end to end. Right? So if you guys want something disruptive, change the optimization strategy. Nature has already done that. Right? Our brain works that way. We don't do end to end. Right? Some of the construction video idea that you can do forward. We are exploring some of that, but we don't have all the pieces yet.
Okay, thanks for the panelists. So let's move to the next question due to the limited time. So the next question actually comes from one of the panelists, Sam. So I mean, the question is, so Richard Sutton argues that the Peters lesson that the most significant advancement in AI have come from simple scaling up computation rather than through human ingenuity, for example, in algorithm design. So the question is, how do we understand the Peters lesson with respect to low dimensionality in deep learning models and AI? And how do you think about the research community on low dimensionality should take the Peters lesson? Yeah, it's a little bit involved. Yeah, maybe again, start from Sam.
Yeah. So this is potentially an interesting question for any field that really tries to build a large edifice, both theoretical and practical around modeling, and also apply all this to large scale data and try to have things work very well efficiently. I think for me, I kind of think about this type of a question like in terms of work that I've done. One thing I worked around that's a little bit connected to vision is kind of invariance in visual data, pose, viewpoint invariance, and things like this. And when you talk about concepts like this, mathematical concepts, in terms of practical, connections to different literatures in deep learning, also vision, a lot of the types of things that you think of historically, at least very recently speaking, are things like these geometric deep learning architectures, where you try to encode certain symmetries into the neural network architecture, have your efficiency in terms of learning, training, what have you, maybe give you some guarantees when you learn these architectures from data, when you apply them at inference time, things like this. I think it's some of the work I've done. So we did some work on this for 3D representation learning, specifically on some of these types of hybrid nerve models. And what you see is that you work very hard. You do a very good job of implementing the invariance. You do a very good job of tuning the optimization algorithm, getting everything to work in concert with one another. You get some gains on things, real world data, because real world data really does have these types of visual, invariant structures. And you get some gains, but So in our case, we had this paper at ICCB and of course, after the submission, SIGGRAPH 2023 sort of Gaussian spotting, really came onto the stage in a very large way. And, so now there's a new sort of representation that becomes the most popular. It has better scaling properties. And just because of these properties, in terms of certain practical applications, in terms of the types of evaluations we see in practice, especially in the academic community, benchmark data sets, it'll blow old approaches, out of the water in terms of the way people are testing. And so the field moves like this very quickly. I think of experiences like that a little bit in terms of the bitter lesson. That's why I thought this is maybe an interesting question for us to think about. And maybe to me, I think that when it comes to theory, when it really comes to efficiency, having a maximally efficient model, machine learning model that uses as much information as you have about the data you're working with, maybe we can ignore the bitter lesson. But if it's really about advancing capabilities and something like general intelligence, I don't know. I'm not sure we can ignore it. And then the question becomes, how can we maybe work around this principle of scaling up computation and how that leads to future developments through low dimensional model, in a way that we don't really just trip over ourselves, have our developments, constantly being outmoded in the next generation. So I don't really have an answer, but that's a little bit how I think about this question in terms of my own experiences and research going forward.
So, I mean, I just want to interpret the question a little bit, right? So should we believe in the scaling law that we scale up the computation, the model size and data that we can gain more performance, or should we put more thought into how to design the model and to break the curse of scaling law? Yeah.
I'm not sure the scaling, okay. But I don't see any AI audience here. I kind of have a mixed feeling about the scaling law. First of all, seems like I personally doing a lot of matrix level, like matrix approximation and optimization. When the matrix becomes larger, seems like a lot of more job for me to do. So kind of like it. But on the other hand, this is also like a fake theorem for me. Because if you look at any function, anything can be locally linear. And then you don't know, go beyond some level if you don't test it. Is it actually scaling linearly still? And if you look back, 2019, the 175 billion parameter model, and we're still at the scale of maybe OpenAI or Gemini is 1 trillion, but that's not really getting more intelligence at this point. Maybe the scaling kind of stops. So for this kind of linear kind of stops here. So I'm not sure we're still at the.
I think that's actually a great point. And actually seeing this question gave me deja vu because I had this exact quote in my PhD defense as well in one of the slides. So it's funny, but I think that in my opinion and in my experience, kind of scaling up and throwing more compute at the problem is the least intelligent and the most easiest way to get more performance, but it's by no means the best intelligently, if that makes sense. So it is true that if you scale up, you are going to get better, but that doesn't mean that this is you couldn't achieve the same level with lower scale if you were to make more clever design choices. And I think that all of the studies on low dimensionality and everything that was presented today, all of those are in line of works that try to achieve, try to embed something that was, achievable in much larger scale in a smaller scale, but making those, theoretically backed up assumptions and, really getting into the details of how we are implementing everything. While just throwing more compute at the problem, yes, it can give you better things, but is that the better, we could have been doing maybe much better with GPT-4 scale up models if we had made more clever choices is what I'm trying to say. So yeah.
I think this visualization should be a two-place support. And I'd like to say that this visualization is true, but true in a certain regime. And this regime is the data-driven. So one famous example is that when the Sora, the video generation comes, people notice that the fabulous generation result, but people also observe that in some certain frames, people observe that objects are not moving by following the physical laws. And this comes to the importance of the knowledge-driven frame. And this is especially important because I think two perspectives. The first is that we know that the human learns knowledge without having so much data collections. And we human are very sample efficient. And not just because that our brain is kind of a pre-trained model, but also we try to learn things by symbolics. The other aspect is that I think there are fundamental difference between the data-driven learning and the knowledge-driven learning. The key is that for the data-driven learning, we know that the data itself encoding a lot of information, and we do not try to extract knowledge from the data. But in many scenarios, in symbolic-driven learning, the data itself doesn't encode any information. For example, we can try to map any initial conditions or initial steps to the steady state or the chaotic state by using different PDs, like naming stocks with different real numbers. So in these situations, the initial conditions or boundary conditions doesn't include any information. But by changing the physical parameters, we can get completely different physical behaviors. And so this is an exact situation that, for example, if we want to generate videos of fluids or smokes or gas, these physical laws, so the PDs actually control the behavior, but we cannot simply use the data-driven methods to fit the initial conditions, which actually doesn't include any information. So I think that this feature layer is important for us to learn, but still within a data-driven scenario. But if we move out of the data-driven scenario, where we really want to use the low-dimensional physical laws to improve our models, then we really cannot follow this feature layer. That's my 2 cents.
Yeah, that reminds me of the recent kind of small experiments my students are kind of doing, kind of interesting to share here. So we know we have a lot of closed models, and then there are like a lot of kind of matches for all the Gemini model to kind of compete with GPT-4o and all the rest, like the rankings, right? And then we're just doing a small test on if you're writing a variable assignment on the logical loops. For example, you can just assign like x equals to 1, x1 equals to 1, x2 equals to 2, x3 equals to x1 plus something. And then you can keep looping it. And how you solve it is like kind of unroll these loops, like how many, the depth of the loop kind of define like how hard or how many computations you kind of have to do to solve this task. And then the kind of y-axis will be like how many problems you get correct under that kind of how many logic loops you have. And then we tested on the different closed models, and seems like that corresponds really well with the ranking of like what people think, how strong those models are. And at the same time, we can like fit a pretty great linear scale on like the slope of how they start to fail, when they start to fail for like loop 1, 2, or like 15. And then like chain of thought and all this, like people claim that they kind of do like more reasoning. And of course, like there are follow-ups saying that if you just replace all these thoughts with like ... you still like get a better result or the same result, right? And then people suspect you are just doing more computation or calculation while you're generating more tokens for those LMs, for example. And then that's how like people think it's like you're trading like computation with how many problems or how complex the problems you can solve. And from that like simple task, I kind of like start to rethink, if you actually know how to solve this problem, you're not constrained to like GPT-4o with chain of thought can solve like loop of 15, which is already very impressive. But at the same time, if you can solve this problem, it's not like you stop at 16 or 18, you can't quantify that. You solve it or you understand it, you solve it. Otherwise you can't. But this is like doing more calculation. But a lot of problems, you can't just purposely do all the calculation and list all the possibilities to solve it, right? So there are 2 ways to view this. Like Wian just mentioned, maybe you can leverage those models to do something that they're good at or they need a calculation to do.
or they can brute force or memorize. And then for like planning or reasoning those problems, you just use like all the other solvers, like people know how to plan. If you kind of can structure the problem to a solver that can understand, and then just use the language model, vision models as some kind of extraction or kind of a translation to a problem that you know how to solve. That's one way. The second way is like what you just mentioned, like you probably need to a fundamentally different way of modeling. Otherwise, you're doing more reports calculations. So yeah, that's just to add up to data driven and all the other methods.
So I suppose, like, I mean, this is not a bitter lesson. I mean, this is something people know about. It scales up, even compressive sensing, as I mentioned, some of the examples, right? You don't even see some of the phenomena until you have enough of that emission is high enough, sample is large enough. I mean, this is one thing, right? So this similar phenomena, when you're scaling something up, so you get a better, it's everything. Okay, it's not just, this is not news. Secondly, is that also you need more computing, more data, and need sensing tools, but this is not the things that will contribute to things other ways that you can secretly improve, right? Or this is necessary. Much of this computing, big fraction of this computing is necessary. So one lesson I learned, right? Even doing the compressive sensing, I guess to remember, even doing solving the same class of problem using first order method, the efficiency can differ by 4 or 5 magnitudes. Okay, the same first order, class of problem. I think we're far from that, right? I mean, right now, this say we just do use the dumbest brute force 3D and it's just scale that up. We're still scaling the same optimization method. That's not necessary. That's not necessarily the optimal thing. So the main aspect of the scaling knowledge is complicated, right? You don't have scaling in this way, right? The slope can be very different. Or if you design a disruptive, a different mechanism, this will be different, right? The right number just in that very local comfort zone, right? And we just think this is the only way of doing it. Is helping some company gets rich. And a lot of people try to convince you this is the only way to by just doing this, we're marching to general AI, right? General intelligence. I completely disagree. I just had an interview recently, right? I mean, if we believe that's the case, I have to change my job. Yeah, we just either change another job. Right? I mean, just wait over AI, just having that tips. Right. So the intelligence will solve, right? So there obviously that's not true, right? Nature does this much more efficiently, and also the current system even has all kinds of limitations. Now we know what they do, right? The transformer does, right? It just compress the data and sample it. So probably they're not even doing the most efficient way of doing it.
Yeah, so I just want to add to Yi's comments, like NVIDIA today surpassed Microsoft, becomes most valuable company in NASDAQ.
That's yeah. Remember, in Gold Rush, who gets rich, right? Yeah, people who know the troubles, yeah. Right? Not the food is rich, not the one, not the gold diggers.
Okay, so maybe you can move to I think the third question. So I think maybe this is could be the last question due to limitation of time, and then I mean this will be a free debate between the audience and the panelists. So the question have several sub questions. So what direction do you think the line of research low dimensionality is headed over the next 5 years? The potential impact. What implications will there be for large-scale vision and language models for data-rich and data-scarce training regimes? Yeah, that's all the questions.
I can say a little bit, at least what I can see. So in terms of, as I said earlier, right? So I think even in terms of extreme low dimensional structures, right? I think the current algorithm, the efficiency of the layer can be significantly improved, right? Even for first order, remember, the lesson we know, even for the simplest class of low dimensional structures, PCA structures, although the operator we do is based on gradient, but the operator is not doing gradient descent, it's actually contracting that. It's power equation, right? So if you want to have iteration converge to a solution within a dozen of iterations, the convergence has to be linear. Gradient descent is too slow. So our brain only have like, less than 10 layers. So if we want to converge something high structural, I think we have to find what are the power iteration like. We can slap on this. And also only see the gradient descent is a problematic because actually the scales is particularly empty space is large, right? It's slower, but the power equation though, right, has nothing to do with where the dimension is embedded. If that structure is embedded, can be embedded in millions of dimensions, right? If you can contract just along the direction, all the complementary direction gets contracted, you're very fast. So we're not there yet. So even in terms of algorithm. The second thing is that one thing is that now we get hold of the structures. The question is how do we get this encoding decoding consistent, right? And you have to learn very consistent encoder decoding. Right now, all this, you can generate text becomes generating images and the videos, but they're not very consistent. Right? It's very hard to control the controllability. That's why there's gazillions of papers about it. Everybody claims they're doing better control, like fine-tuning this and that, right? We don't understand, how do we sample that distribution in a very consistent, very controllable way. I think that will be one of the major problem and I'm become very optimistic. Indeed, a lot of things that if we read, text is actually simple, right? Compared to images and videos to the 3D, right? So the larger information the data gets, you really want efficiencies, right? And hence requires that the algorithm has to be more scalable, right? And you just cannot do the same thing. It's the same kind of transformer for videos and so on. Those are much more expensive to do. The reason why now we're doing some video producing, but they're very limited domain. They're very limited scope of data size. So I think that if you apply this method to higher dimensional data, higher resolution, and you do need much more efficient low dimensionality thinking, exploring the low dimensional structure in the visual data, high dimensional visual data, better and better in order to scale. Right? Text is just a one dimensional, discrete variables. So.
Yeah, so this is a free debate. Just feel free to ask the panelists or just raise your own opinion.
I think one thing that I wanted to add, I wanted to tie this a little bit to the previous question. I think, especially about the potential impact, something that really excites me about this line of work is that it's not blinded by scaling up or doing more compute. So it's really tied into making thoughtful changes and improvements. So I think that it has a lot of potential to make impact because there's not that gold digging rush to kind of create the next big thing. But in terms of how it can be used for large scale vision and language models, I think I'm excited to see some upcoming work on explainability that use low dimensional models, and also some other aspects that could potentially be very exciting. And I think Professor Ma also touched on this subject is local improvements to the model instead of doing end-to-end updates and continual learning. If we can empower this with low dimensional models, that'll be great. And yeah, I think I just That's just my thought.
What I've understood is Professor Ma said that, first I totally agree that if you want to make some steps further, you probably need some very revolutionary candidates proposal of innovation method and candidates. I also want to put an add-on something that I think at this moment it seems to be more challenging for us to do this kind of change. Because obviously the industry players will definitely keep going on this scaling up, and since we are already building very powerful models, if we want to take different ways, we need to convince people in the industry, which is very difficult to convince. And also consider that we already invested tons of money in building these models. I think it's more challenging for them to turn over all more maybe we could review and take our suggestions. At this moment, it's very hard for us to do.
That's also been very challenging for us. I mean, usually we think you have better ideas, but these days you have to, right? It's not enough just to, prove the theorem and prove that your idea is right. A proposal algorithm, you test on a small scales, think that it works. So it's become less convincing. It's a little bit frustrating for research academia, I believe. But that's why in the past couple of years, we are test, I just try with our limited resource to push to the scale where hopefully will be more convincing to people, including some of the experiments you saw here we did in our recent work. It's really not necessary for us because, but we did it nevertheless, tested out almost all the scenario, right, that the transformer has used. He said it's MAE, Dino, and HTTP, the BERT. At least to the point where the scale we can afford is a couple hundred cars, right, or thousands of cars, like that. But it helps. I mean, to see the people they can actually get to. I do encourage, probably younger folks, you just do theory. Probably this stage is not enough to convince people. You do have to do a little bit additional empirical evaluation because the industry are used to that kind of evidence rather than just take the ideas, right? But on the other hand, that I don't think that the academias should follow the same lines of research, right? See, just because if you work on aerodynamics, you don't have to do the volume 24/7 to prove that you actually, right? You can work on drones, right? You can work on other things, right? On birds fly, right? So I mean, there's many different opportunities out there, especially for researching academia. Just forget about it. You cannot just compete. If you follow the same line of technology or method, it's a losing battle, right? You have no added value whatsoever. So we have to be more ingenious in terms of looking for the right problems or a better method to have the value added.
Yeah, so before we proceed with the panelists, maybe give the audience
For the experiment. And I have a question to ask for two. And I think another desirable property for representation or features in learning representation learning is that the disentanglement of the feature. So what do you think is the relationship between the property of loaded regionality and the disentanglement? If learning is pursuing loaded regionality automatically leads to the disentanglement, or do you think there's any other relationship? Thank you.
Yes, so in the sense that trying to identify these low dimension structures and just compress what's clusterable correlated, and also expanding different things that kind of have a tendency of doing that. Right? Be able to disentangle what is independent, making even dependent things independent, coherent things. Right? If you have various reasons, evidence, then it should be that simple. Right. The current actually rate reduction information gain actually has that. If you think about it, it's going to measure that, to promote that kind of disentangle. And also in the group, right? You have to find the optimal data are incorporated. That global optimal has this subspace are the clusters at least. But whether or not your data allows that, that's a different story. That's back to my original comments. We don't know yet what is the joint distribution, what the proper assumption we should make. That could be largely there are separable, but there's still correlations, right? Between classes and images. So that's actually one of the things I think the theoretician has to work out, what the proper assumptions of the data distribution. So that when we mean precisely what we mean, what is this tangled, can be seen tangled, what cannot? What if they're not, then how we going to represent them? It's still very structured rather than all separate substrates. That's just my.
Any comments from the panelists?
I think, let me just say briefly, I think disentanglement in a supervised versus an unsupervised sense, I totally agree with you. I think mathematically it's going to be difficult to define precisely what disentanglement should be. Certainly it's different between those two regimes. And if you think of like POI cases, I feel like you run into paradoxes pretty quickly. Like if I have some structured data, low dimensional structured data, and it's a pair of subspaces, here they are. At what point, like as I correlate these subspaces more and more, and I ask you to obtain a disentangled representation for me, we can talk about doing this with MCR. We can talk about doing it with contrastive learning, invariant risk minimization, our favorite thing. At what point, like, should these subspaces be combined? And at what point should they be disentangled? If they're here, do you want this representation or this one? What would MCR do? What would contrastive learning do with this network, that network? I mean, these are all questions one could ask. But I feel like fundamentally there's kind of a paradox here. A lot of it feels like, to me, I agree with you. You really have to do some modeling, I think. Model what these structures actually are. Because without any type of grounding, I don't think it's possible to really resolve that paradox. And then for me, if I think about things like disentanglement in visual data or something like that, you know, talking about pose and appearance or shape and things like this, it's very interesting, I think, to think about whether or not it's possible to disentangle these in an unsupervised way. I only know of work that can do it provably in a supervised sense. And I think if you talk about doing this in an unsupervised sense, it feels to me like it starts to connect to some of these issues we were talking about in the previous questions about differences between reasoning and like empirical or data knowledge. I think that's something that would be very interesting to explore more theoretical level.
Yeah, I mean, from the practical point of view, if you, another way is just to measure why do you want to disentangle? What do you mean by that? How do you measure, you know, tangling, disentangle? Right? What the representation is well, measure. Because the information being has kind of really back and try to do that top down, right? Give me a representation, there is some evaluation. Just like entropy, right? It's a measure of information. That's the volume, size, or number of bits. So you have to sort of measure. One question is, right, a lot of questions that you ask something very basic. Why do you do that, right? And why do you want to disentangle? And what do you mean precisely mean by that? Can you measure that? So that will probably help you to address, make those problems well conditioned, well defined.
Nature of work, and basic exploration, which should be forward, should be forward variance. Actually, I just have exactly the same idea described in a paper I recently published. I came to CDPR is more to introduce this word as a system for operations. The way to talk further after this.
Sure. Thank you. I think, if you really, I think it's time, right? We know, I mean, we have stuck in this one regime, we optimize the network and also doing a global optimization that is global descent, application, and so on. We're been stuck in that local minima for quite a long time, right? And, yes, you can keep scaling it and keep doing this, but really that's not what I call not natural. categorize optimization into 4 categories. One is that are things computable, tractable, scalable, and natural. Right? Even one is scalable, it may not necessarily natural. Right? Gradient descent is scalable, but that's global gradient descent is done for the nature kind of event. Right? And hence, what property of the data, I don't know what kind of information that one architecture allows you to, because it allows you to do very local incremental updates, but yet globally you can converge to something so remarkably efficient. Right? And it must be at least to me, it should be work together with forward, backward, right? Local forward, backward, we can send to do corrections, sub-corrections, much more efficiently, and layer-wise, also probably, right, adjacent neurons, communications with each other. And the neurons do have all the other, they have the interpretation behaviors, why, we don't know, right? So there's all kinds of other mechanisms that we can apply. So maybe it's very different optimization strategy, right? Really allows to end up with a more efficient, at least energy efficient mechanisms. So that is really, I think, the future for it's right, at least for research, for universities or for academia. Industry can do whatever they want, right? Whatever they can make money out of, right? But I think it's a great time for us to, I think, to find and divide better directions. Right?
Okay, so we are almost at time. So I think I will leave the last question to the audience and then we wrap up from here. Any comments, questions from the audience?
Any suggestion how we could improve the tutorials?
Yeah, that's welcome.
Okay, can you speak louder? It's very hard for us to think about
the robustness of neural network, as you know, neural network building about against smart perturbation, associated perturbation. And there is some methods that use it in robustness to build a robust model against adversarial attack. Maybe the data and over the dilution can help us to improve this models maybe.
Yes, I think so. So that's a particular mystery, right? See, there's a lot of initial people always think that people interested in robustness, or there's a lot of issues with sensitivities, the unstability, but we just stop talking about that. I don't know, as if those problems have been solved. No, they're not, right? It's kind of weird, but now everybody's talking about scaling things up as if those problems will be solved. In fact, it's actually getting worse, right? Robustness, beginning of the recent study that, you know, catastrophic forgetting, nothing goes away, right? A lot of issues, the robustness issue, adversarial attack is still there, right? Including the big models actually worse, actually, reports. But nobody, you know, very few people seems to take them seriously. Even robust, the adversarial robustness people, a lot of people take the study, but somehow still the existing solution is still very expensive, and somehow get stuck. And somehow, even I think Yao Dong is not here. Yao Dong worked on this earlier with Michael Jordan and those guys. Game, you know, minimax game theory approach, right? But somehow that is stopped. I don't know why. As if the problem, no, it's not solved. I don't know.
Maybe the progress gets.
Yeah, the progress gets stuck.
Yeah.
Right. Also, even the invariance problem, right? It's not solved. I mean, now people just, oh, it's just all of them more. No, I all of them more. Yeah, good there. The definition actually still, you know, you can still, it's not environment.
Yeah.
Somehow people just
commercial incentives too, right? Like most of us aren't becoming full track tenured professors.
Yeah.
So you're gonna go to industry, every single job post, everybody in this room knows exactly who's hiring for what. Right now it's generative AI. I can't stand that personally, but you have to graduate, you have to get a job, you have limited time. You start thinking, okay, well, is adversarial robustness gonna get me a job? Is no, it's terrible and it's crappy, but there's this enormous industry incentive that's leading the research down these very limited and potentially not very productive paths.
And I agree, but that's also, but I believe, I work at Hong Kong University, a lot of data science institute, a lot of young faculty, there's a lot of stress, also anxiety, what they should work on. If I don't have 100 cars, 500 cars. I'm the director of the department, like, how's they get a request? Oh, we want to have 100 cars. I said, nobody gets 100 cars. Everybody at Berkeley, nobody gets 100 cars, right? So you have to, then the job is to identify what is worth the research on, right? Even all the generative models, right? Have anyone really tested them carefully? No, right? Everyone talk about, industry 4, this is going to be fantastic, right? But if you do a little testing, image-based generation, they are horrendous, right? You cannot even generate the correct number of objects. Right, right? It's very simple test. So I'm somehow, as a, as our standard is very low now, right? It's just some successful cherry picked example. Somehow we think the problem is so nice, right? But it's just our basic scientific engineering training. You just apply to test, collect some statistics first time the information. It's not that great, right? So, certainly we have a report with John and Simon about this. Evaluating this multi-model, we call it eyes wide shut, right? Because all this, open source or even GPT-4 and also Gemini, very basic or common sense questions. They're prolific. They're no better than random tests. Right? Also, they have long conditional generations. We're very, very not consistent at all, this test. But some, of course, you can generate, with $1 billion, throw out a big data models trained on billions of images. Of course, you can pick up images that generate pretty well, right? But in terms of very, very level of performance, right, the kind of consistency or controllability, it's actually pretty bad. There's a lot of things to something fundamentally wrong, but somehow the whole community, the younger folks, is doing fine tuning, right? I just don't understand it. Right? So, everybody, all the faculty said, oh, we can improve this by fine tuning that. Try to identify exactly. So they're trying to identify that fundamentally wrong. Why it's fundamentally wrong, right? So I think those are the great opportunities for this research, right? Don't just because you can find a job, right? So,
I think just one thing I wanted to add is, as someone who did adversarial robustness in their PhD, I still got a job.
I did out of distribution to say.
But one thing that I wanted to add was, I feel like at some point it's gonna get saturated, and I just wanted to maybe give a little bit of hope to all the students sitting here. Working on those a little bit more creative problem, things like, adversarial robustness, or thinking a little bit outside the box of just fine tuning. I think that at the end of the day gives you a little bit of edge over all the other applicants as well, because at the end of the day, you're gonna hit a wall with the way that you're going, and that's not that far off, maybe a year, 2 years, but we'll get there. And then at least working on these diverse topics can give you, it helps you gain a new perspective to be able to push the field further. I feel like, so yeah, just a little bit of hope.
Yeah, it's an exciting time actually. That's right. It's just a lot of those new observations and just backs for much better understanding, much better, angles. And if you look at the history, especially in the 1940s, I'm doing a lot of look at the history of intelligence. It's just so much. The ideas are so much diverse, richer. And the interesting intelligence-inspired control theory, information theory, game theory, right, cybernetics, and even the later artificial intelligence, right? And we don't see that anymore, right? In this era, yet we have a huge community, and somehow everybody's doing the same thing. Right? 10,000 papers and how many really, genuine ideas. Right? So that we become very homogeneous in terms of research that, intelligence is very diverse. Right? And don't let that, the popularity or fashion that you see that this is actually exactly the opposite. I think this is the era that's for much deeper understanding of intelligence, rather than just be led by technological, the scaling up compute, right? But yes, of course, scaling up helps, right? Anything helps. But any scaling up helps. But then it's that, are you scaling up the right method? Are you scaling up the right system? Right? Are you really getting what you should get? That is the question we should to ask more.
Yeah, so I want to add a little bit to the robustness question. So actually, so low dimensionality actually helps. I mean, recently we have a work on SML. So actually we can deal with this label noise by using this very simple idea from robust PCA. So remember from robust PCA. So the low dimensional structure can be exactly separated from the sparse noise, right? So actually we just incorporate this kind of simple idea that we can design a very simple method to deal with this kind of label noise that we achieve the best result on the benchmark, just to do a little bit like modification of this kind of robust PCA idea. And this is a like work, I think, with Chong and Yi several years ago. And then we also test this on label noise, the kind of scenarios.
Classical
And Zhihui, yeah.
Right. So I mean, one of the work I showed is a robust face recognition. Right. You can crop the image. So basically, you can identify the low dimensional structure correctly. Right. See, low dimensional structure is the only thing you can rely on to do denoising correctly, to do completion correctly, to do error correction correctly. Right. Actually, think about it. And actually, that is actually not only the way to test it if you get the correct low dimensional structure. You can denoise, you can complete, you can predict, you can actually do outlier rejection, robustness. It's probably the only thing you can rely on. And turns out that those are also cases that you use to retrain the model. Denoising, completion, prediction, text token. Right? Precisely, that's also the things you relies on. The low dimensional structure to train. And also it's a check. Have you got the low dimensional structure correctly? Right. So I
Okay.
down. Everybody to leave the property. Building's been shut down in about 15 minutes. All right, cool. Next.
Okay, so thanks for everyone attending. Thank you. Thank you.